Imagine a world so dark that it almost disappears against the blackness of space. A planet that barely reflects any light, making it nearly impossible to detect. A place where even the most powerful telescopes struggle to find a trace of its existence. These are low-albedo exoplanets, planets so dark that they absorb almost all the light that reaches them, leaving astronomers baffled as to why they exist and what secrets they might hold. Why are these planets so dark? What are they hiding beneath their pitch-black surfaces? And could they challenge everything we thought we knew about planetary science? When we look up at the night sky, most of what we see is light, reflected from stars, planets, and moons. But what about the things we don't see? Space is already a place of mystery, but low-albedo exoplanets take that mystery to a whole new level. Unlike Earth, which reflects about 30% of the sunlight that hits it, or even Jupiter, which reflects about 50%, some of these planets reflect less than 1%. That means if you were floating in space near one of them, you might not even see it at all. It would be like staring into a void, a massive celestial body right in front of you, and yet it would remain invisible. Scientists have found a few of these dark worlds, but even those discoveries were difficult. Traditional methods of detecting exoplanets often rely on measuring the light they reflect, but these planets don't reflect much at all. Instead, astronomers have to look for other clues, watching for dips in a star's brightness when a planet passes in front of it, or using special instruments to analyze the faintest traces of light they do give off. But what makes these planets so dark? That's where the real mystery begins. One of the most famous low-albedo exoplanets discovered so far is Trace 2b, a gas giant about 750 light-years away. This planet is darker than coal, reflecting less than 1% of the light that hits it. To put that in perspective, the darkest material on Earth, vantablack, reflects around 0.035% of light. Trace 2b is even darker than that, making it one of the least reflective objects ever found in space. But why? What makes it so black? The answer isn't as simple as it might seem. Scientists believe that a planet's darkness is linked to its atmosphere and the materials it's made of. On Earth, we have clouds, oceans, and ice caps that reflect sunlight, making our planet relatively bright. Even gas giants like Jupiter have clouds of ammonia that scatter light. But on planets like Trace 2b, the atmosphere is different. It's thought to be full of chemicals that absorb light instead of reflecting it. Substances like vaporized sodium, potassium, and titanium oxide could be trapping light within the planet's thick, sweltering atmosphere, making it appear nearly invisible. But here's where things get even weirder. While Trace 2b is almost completely black, it's not entirely black. Scientists studying the planet found that it glows faintly red, like burning embers. This is because the planet is incredibly hot, far too hot to support life as we know it. It orbits extremely close to its star, with temperatures soaring above 1,800 degrees Fahrenheit, 980 degrees Celsius. At such high temperatures, any reflective clouds that might have formed would be burned away, leaving only an atmosphere filled with light-absorbing chemicals. But even then, it doesn't explain why the planet is so dark. There could be other unknown processes at work, things we don't yet understand about planetary formation and atmospheric physics. And Trace 2b isn't the only one. Astronomers have found other planets with similarly low reflectivity, hinting that there may be many more out there, lurking unseen in the depths of space. Some of these planets are thought to be covered in tar-like substances or complex hydrocarbons, which could contribute to their darkness. Others may have surfaces made of unknown materials that swallow up light like a cosmic black hole. But here's the real question: if there are planets this dark, could there be planets even darker? Could there be entire worlds hiding in the darkness of space, undetectable with our current technology? The more we discover about low-albedo exoplanets, the more questions arise. Are they rare, or are they more common than we think? Could there be Earth-sized low-albedo planets that are practically invisible to us? And if so, what could be on their surfaces? These planets force us to rethink how we search for exoplanets. Traditional methods rely on light, but if a planet doesn't reflect any, we might not even know it's there. That means we could be missing an entire category of planets, hidden, dark worlds that slip through our detection methods like shadows in the void. Some scientists are now looking at new ways to find these elusive planets, using infrared telescopes to detect their heat signatures or searching for gravitational effects on nearby objects. But even then, the challenge remains: how do you find something that refuses to be seen? And then there's the question of what these planets could mean for the search for extraterrestrial life. Most of the exoplanets we've found so far have been detected because they reflect light, but if low-albedo planets are more common than we thought, it means there could be far more planets in the universe than we've ever imagined. And if there are more planets, then statistically, the chances of finding life go up. But what if life on these planets is different from anything we've ever expected? What if low-albedo planets harbor forms of life that have adapted to exist in near total darkness? Could there be organisms that thrive in an environment where almost no light reaches the surface? There are still so many unknowns when it comes to these strange, dark worlds. Every new discovery raises more questions, pushing the boundaries of what we know about the universe. And if we're missing an entire category of planets simply because they don't reflect light, what else could we be missing? Could there be planets made of materials we've never seen before? Could there be worlds that are invisible not just to our eyes but to all our instruments? The search for low-albedo exoplanets is only just beginning, and as our technology improves, we may uncover even stranger things lurking in the cosmos. But for now, these planets remain among the greatest mysteries of space, massive, hidden, and waiting to be discovered. The idea that there could be countless invisible planets drifting through space is both fascinating and unsettling. It forces us to confront a major limitation in our understanding of the universe. We tend to only recognize what we can see. But low-albedo exoplanets defy that logic. They challenge the way we search for planets, the way we define what's common or rare, and even the way we think about habitability. If we've already found a handful of these dark worlds with our current technology, how many more are slipping past us undetected? Could there be entire planetary systems filled with nearly invisible worlds, orbiting distant stars without leaving any trace? One of the biggest mysteries about low-albedo exoplanets is what exactly makes them so dark. Scientists have theories, but they don't yet have all the answers. Some of these planets may have atmospheres full of complex molecules that absorb light, while others may have surfaces covered in unknown materials. But what if there's something even stranger going on? What if these planets have entirely different compositions than anything we've ever seen? Could they be made of exotic elements, substances that interact with light in ways we don't fully understand? Take Trace 2b, for example. We know that it's one of the darkest planets ever discovered, but the exact reason remains unclear. Its atmosphere contains things like vaporized sodium and potassium, which absorb certain wavelengths of light, but those elements alone don't explain why it reflects almost nothing. Some scientists suspect that there could be other, more complex chemical reactions happening in its atmosphere, perhaps involving high-temperature compounds that have never been observed in a natural environment before. And then there's the question of its faint red glow. Could there be processes happening on this planet that generate their own light? If so, what does that mean for our understanding of planetary atmospheres? But let's go beyond Trace 2b. It's just one example of a low-albedo exoplanet, and if there's one, there must be more. In fact, there could be entire classes of planets that are just as dark, or even darker. Imagine a world where the surface is made of a material so absorbent that it acts like a sponge for light. A planet where even the faintest glimmers of starlight get swallowed up the moment they touch the ground. What would that kind of planet be like? Would it be a dead, barren wasteland, or could it have a unique ecosystem adapted to the darkness? The more we think about low-albedo exoplanets, the more we realize how little we know. Astronomers have spent decades refining their methods for detecting planets, but those methods are built around the assumption that planets reflect at least some light. When we find objects that barely reflect anything at all, it exposes a major blind spot in our search. It means there could be countless planets we've missed simply because they don't behave the way we expect them to. And then there's the question of habitability. Most of the time, when scientists talk about habitable planets, they focus on things like temperature, atmosphere, and whether liquid water could exist. But what about planets that are permanently shrouded in darkness? Could life evolve in an environment where there's almost no light at all? On Earth, we tend to associate life with sunlight. Plants use it for photosynthesis, and most animals depend on vision to navigate their surroundings. But life on Earth is also incredibly adaptable. There are creatures in the deep ocean that live in complete darkness, surviving off heat and chemical energy instead of sunlight. If life can exist in the lightless depths of Earth's oceans, could something similar exist on a low-albedo exoplanet? What if there are entire alien ecosystems that have evolved without ever seeing a ray of sunlight? Could there be organisms that generate their own light, like deep-sea bioluminescent creatures? Could there be completely new forms of life that function in ways we can't even imagine? If low-albedo planets are as common as some scientists suspect, it could mean that the conditions for life are much broader than we previously thought. It would expand the definition of what a habitable planet looks like and force us to reconsider how and where we search for extraterrestrial life. But even if these planets aren't habitable, they still raise enormous questions about planetary formation. How do they end up so dark? Are they born that way, or do they change over time? Could some of these planets have started out as bright, reflective worlds, only to become darker as their atmospheres evolved? Or could there be external factors, like collisions with other planets, exposure to extreme radiation, or interactions with their host stars, that cause them to develop these strange, light-absorbing properties? Another thing to consider is how these planets impact their surroundings. Even though they don't reflect much light, they still have mass, gravity, and an influence on their star systems. Could they be affecting the orbits of nearby planets without us realizing it? Could they be distorting the paths of comets and asteroids in ways we haven't accounted for? If we're missing a large number of low-albedo planets in our surveys of the cosmos, it means we could also be underestimating the gravitational dynamics of entire star systems. And then there's the possibility that some of these planets aren't just naturally dark, but intentionally hidden. It's a wild idea, but one that some scientists and science fiction writers have considered. What if an advanced civilization had the technology to make a planet nearly invisible? Could they engineer an atmosphere that absorbs all incoming light, effectively cloaking their world from detection? If such a thing were possible, a low-albedo planet could be the perfect place for an advanced civilization to hide from prying eyes. It's an extreme idea, but one that fits into the larger mystery of why these planets are so difficult to detect in the first place. The search for low-albedo exoplanets is still in its early stages, but it has the potential to completely reshape our understanding of the universe. These planets show us that the cosmos is far more complex and mysterious than we ever imagined. They force us to confront the limits of our detection methods, question our assumptions about planetary composition, and rethink how we search for life beyond Earth. And the more we learn, the more we realize just how much we don't know. As telescopes become more advanced, we may finally start uncovering more of these hidden worlds. Upcoming space missions, like the James Webb Space Telescope and next-generation planet-hunting observatories, could give us the tools we need to study these dark planets in greater detail. We may eventually develop new ways of detecting planets that don't rely on reflected light at all, perhaps by looking for their infrared signatures, gravitational effects, or even their interactions with interstellar radiation. But for now, these worlds remain some of the most elusive objects in the universe. They are the shadows between the stars, the unseen travelers of the cosmos. They remind us that space is still full of secrets waiting to be uncovered. And as we continue our search, one thing is certain: the universe is far stranger than we ever imagined. The deeper we dive into the mystery of low-albedo exoplanets, the more we realize how much we are missing in our understanding of the universe. The fact that we have already identified a few of these nearly invisible worlds suggests that they may not be rare at all, just difficult to detect. This raises an important question. If we have only found a handful of them using our current technology, how many more are out there, completely slipping past our radar? Could there be an entire population of planets, larger than anything we've accounted for, existing right under our noses? One of the biggest challenges in studying these planets is that they don't follow the traditional detection methods that astronomers rely on. Most exoplanets are discovered through the transit method, which looks for tiny dips in a star's brightness as a planet passes in front of it. But what if a planet absorbs so much light that the dip in brightness is nearly undetectable? What if its presence is so subtle that we mistake it for noise or ignore it altogether? There's also the radial velocity method, which detects planets by measuring how their gravity slightly wobbles their host star. While this method doesn't rely on a planet's brightness, it still has limitations, especially if the planet is too small, too far away, or moving in a way that makes its gravitational influence harder to detect. But what if low-albedo exoplanets aren't just outliers? What if they represent a fundamental part of planetary formation that we have overlooked? For a long time, astronomers assumed that most planets would have at least some reflectivity. After all, even the darkest objects in our solar system, like the Moon or Mercury, still reflect a portion of sunlight. But now, with planets like Trace 2b challenging those assumptions, we're forced to rethink what's normal. What if a significant percentage of exoplanets are just as dark, or even darker? What if the average planet in the universe isn't a bright, colorful world, but instead a black void, absorbing almost everything that touches it? To truly grasp the implications of this, imagine an alternate version of our own solar system, one where most planets are covered in material that swallows light instead of reflecting it. What if Earth itself had evolved with an atmosphere so thick and dark that sunlight never reached the surface? Would life still have developed? If so, would it have taken an entirely different form, relying on heat and chemical energy instead of photosynthesis? Could complex civilizations have emerged in a world where sight was never an option? These are the kinds of questions that low-albedo exoplanets force us to consider. One of the most intriguing possibilities is that these planets could have exotic atmospheres unlike anything we've ever seen. On Earth, we see a wide variety of atmospheric compositions, from the nitrogen-oxygen mix that makes our planet habitable to the thick, crushing clouds of Venus. But what if there are atmospheres out there composed of elements or compounds that behave in ways we can't yet predict? What if some planets have air so dense that it bends light, trapping it instead of allowing it to escape? What if their skies are filled with microscopic particles that absorb every incoming photon, making the entire planet appear as a featureless black sphere from space? And if we do eventually manage to observe one of these planets up close, what would we see? Would its surface be completely devoid of features, like a smooth, matte black orb floating in the void? Or would it have a strange, textured landscape, covered in materials that actively consume light? Could there be unknown minerals that make up the crust of these planets, substances that we have never encountered on Earth? Then there's the question of heat. Even if a planet absorbs almost all visible light, that energy has to go somewhere. On Trace 2b, scientists have noticed a faint red glow, which suggests that the planet is re-emitting some of that absorbed energy as infrared radiation. But what if there are planets that take this even further? What if some of these low-albedo worlds become so efficient at absorbing light that they heat up far beyond what we would expect for their location? Could this lead to extreme weather patterns, atmospheric storms, or even conditions so chaotic that they make these planets uninhabitable, even for the hardiest of life forms? Or, on the opposite end of the spectrum, what if there are planets that are so dark and so cold that they absorb light without re-emitting much of it at all? Imagine a planet so effective at trapping energy that its surface remains near absolute zero, a frozen wasteland barely above the temperature of deep space. Could such a world exist in a stable orbit around a star, or would it have to be a rogue planet, drifting through interstellar space, absorbing the faintest traces of radiation as it moves? If so, could there be planets that are effectively invisible not just to the human eye, but to almost all forms of detection? The concept of rogue planets, planets that have been ejected from their star systems and now wander alone through the cosmos, adds another layer of mystery to low-albedo exoplanets. If a rogue planet were also a low-albedo planet, it would be almost impossible to see. It wouldn't emit its own light, and it wouldn't reflect much of the light it encounters. It would be a true ghost planet, drifting through the darkness, completely undetectable unless it happened to pass in front of a distant star or interact gravitationally with other celestial bodies. How many of these invisible wanderers could be out there? Could there be more rogue planets than there are stars? And then there's the ultimate question: Could any of these planets support life? If life exists on Earth in deep ocean trenches, thriving without sunlight, could something similar happen on a dark exoplanet? What if alien life forms have evolved in conditions where they never needed eyes, instead relying on sound, heat, or even electromagnetic fields to sense their environment? Could there be creatures that navigate purely through touch or pressure changes in the air? What if entire ecosystems exist beneath the surface of a low-albedo planet, hidden away in vast underground oceans? We already suspect that icy moons like Europa and Enceladus might have subsurface oceans capable of supporting life. So what if the same is true for dark exoplanets? Could these hidden oceans be home to vast, sprawling networks of alien organisms, living in ways that defy everything we know? The deeper we go, the more questions arise. The mystery of low-albedo exoplanets isn't just about discovering new worlds. It's about reshaping our entire understanding of what a planet can be. It's about acknowledging that the universe is far more complex and unpredictable than we ever imagined. Every time we think we've figured out how things work, we stumble upon something that forces us to reconsider everything. We are still in the early days of exoplanet exploration. The technology we have now is powerful, but it's only scratching the surface of what's out there. As we continue to develop more advanced telescopes and detection methods, we may start to uncover more of these mysterious planets. We may finally start to understand what makes them so dark, what they're made of, and whether they could host life. But for now, they remain one of the greatest cosmic enigmas, silent, hidden, and waiting to be discovered. The existence of low-albedo exoplanets forces us to confront a disturbing reality. The universe may be hiding far more than we ever imagined. If entire planets can effectively disappear into the darkness, then what else is out there that we simply haven't detected yet? Could there be entire solar systems filled with planets so dark that they evade all our methods of observation? Could we be looking at the wrong places, using the wrong tools, and making assumptions that blind us to an entire category of celestial objects? To answer these questions, we need to rethink our approach to finding exoplanets. Right now, the most successful method is the transit technique, which looks for small dips in a star's brightness when a planet passes in front of it. But what if a planet absorbs so much light that the change in brightness is almost negligible? What if the contrast between the star and the planet is so extreme that even the most sensitive instruments can barely detect it? If this is the case, then there could be an enormous number of undiscovered planets lurking in the void, planets that we've missed simply because they don't reflect enough light to catch our attention. Some scientists have proposed using infrared telescopes to detect these dark worlds. Since all objects emit some form of infrared radiation based on their temperature, even a planet that absorbs almost all visible light should still give off a faint heat signature. This is how we've been able to confirm the existence of some low-albedo exoplanets, like Trace 2b. But what if there are planets that are so efficient at absorbing and retaining heat that they barely emit any infrared radiation at all? Could there be worlds so dark and so cold that they are functionally invisible to all of our current detection methods? The implications of this are staggering. It would mean that we have only scratched the surface of what exists beyond our solar system. It would mean that the number of planets in the universe is far greater than we currently estimate, perhaps even orders of magnitude higher. It would also mean that our understanding of planetary formation is incomplete. How did these planets come to be? What conditions create a world that absorbs almost all light? Are they simply the result of unusual chemical compositions, or is there something more at play? One of the most fascinating possibilities is that some low-albedo exoplanets might have atmospheres filled with exotic compounds that absorb light in ways we don't fully understand. On Earth, we are familiar with gases like methane, carbon dioxide, and nitrogen, which shape our atmosphere and influence our climate. But what if other planets have atmospheres composed of elements, or molecules that don't exist naturally on Earth? What if some of these planets have developed atmospheric layers that act as perfect light traps, capturing every photon that enters and preventing any from escaping? Such an atmosphere would create a world of eternal darkness, a place where the sky is always black, even in broad daylight. Imagine standing on the surface of a planet like this. There would be no sun in the sky, no stars, no moonlight, just an endless, featureless black voids stretching in all directions. Would such a world be completely lifeless? Or could some form of life evolve to survive in these conditions? Could organisms exist that don't rely on photosynthesis, instead deriving energy from heat, chemicals, or even magnetic fields? Some scientists speculate that low-albedo exoplanets might be ideal candidates for discovering entirely new forms of biology, life that operates under principles completely different from anything we've seen on Earth. If life has evolved in total darkness, it might have developed sensory adaptations that are unlike anything in our known biosphere. Perhaps organisms on these planets use sonar-like echolocation, similar to bats and dolphins, but far more advanced. Maybe they can detect electromagnetic fields, sensing their surroundings in ways we can't even imagine. And then there's the possibility that some of these planets aren't just naturally dark, they might be artificially dark. This leads us to one of the most intriguing and controversial questions in the search for extraterrestrial intelligence. Could some of these planets be deliberately engineered to be invisible? If an advanced alien civilization wanted to hide its presence from the rest of the universe, covering an entire planet in a near-perfect light-absorbing material would be an excellent way to do it. Some scientists have speculated about the idea of stealth planets, worlds that have been intentionally designed to avoid detection. Such a civilization might have reasons for doing this. Perhaps they fear hostile extraterrestrial forces and want to remain hidden. Maybe they are observing other civilizations without interfering, ensuring that they leave no detectable trace. Or, more intriguingly, what if these planets serve as vast, artificial energy collectors, absorbing light to power some unknown megastructure or advanced technology? If this sounds far-fetched, consider this. We already use light-absorbing materials in our own technology, such as vantablack, a substance that absorbs 99.96% of visible light. If human beings have already developed materials that can dramatically reduce reflectivity, then a civilization that is thousands or millions of years ahead of us could have perfected the process on a planetary scale. This idea brings us to the concept of Dyson spheres, hypothetical megastructures built around stars to capture their energy. If a civilization is capable of constructing a Dyson sphere, it might also be capable of covering entire planets in an energy-absorbing shell. Perhaps some low-albedo exoplanets aren't just planets, but massive power stations, harvesting starlight for unknown purposes. Of course, this is all speculation, but the mere possibility that some low-albedo exoplanets could be artificial should be enough to make us reconsider how we approach exoplanet detection. If we are only looking for planets that reflect light, then we might be missing out on some of the most fascinating discoveries in the universe. At this point, one thing is clear: the search for low-albedo exoplanets is not just about finding new planets. It's about uncovering a hidden aspect of the cosmos that has remained invisible to us until now. Every discovery we make challenges our assumptions and forces us to ask deeper questions. What else is out there? What other secrets are hidden in the darkness? As technology advances, we will develop better ways to study these planets. The James Webb Space Telescope has already opened new frontiers in exoplanet research, allowing us to analyze atmospheres and surface compositions in unprecedented detail. Future telescopes, like the proposed LUVOIR or Habitable Worlds Observatory, could give us even clearer images, revealing details that are currently beyond our reach. One day, we might finally get a close look at one of these mysterious, dark worlds. When that happens, we could discover something that changes everything we thought we knew about planets, about life, and about the universe itself. Until then, low-albedo exoplanets remain one of the greatest mysteries in space, silent, unseen, and waiting to be found. The discovery of low-albedo exoplanets has forced us to rethink the way we perceive the cosmos. Traditionally, when astronomers searched for exoplanets, they relied on the brightness of stars and the way planets reflected light. But these dark worlds challenge that assumption. They exist in the shadows, absorbing almost all the light that reaches them, making them nearly undetectable with conventional methods. If these planets are more common than we realize, then our current estimates of how many planets exist in the universe could be wildly inaccurate. The sheer number of undiscovered worlds could be staggering. Right now, our knowledge of exoplanets is limited to those that we can detect using the transit method, the radial velocity method, or direct imaging. But if a planet reflects almost no light, it might not produce the typical signals that these methods rely on. This means there could be an entire class of exoplanets that remain hidden, simply because they don't interact with light in the way we expect. Some scientists have suggested that instead of relying on optical telescopes, we should be focusing more on infrared observations. Even the darkest planets should emit some level of heat, and instruments like the James Webb Space Telescope are designed to pick up on these subtle heat signatures. However, this presents another challenge. What if some of these planets are so good at absorbing and retaining heat that they barely emit anything detectable? If a planet's atmosphere is composed of materials that efficiently trap heat, it could remain at a temperature that doesn't stand out against the cosmic background, making it even harder to detect. But let's assume we do find more of these planets. What would they be like? The first thing to consider is the surface. A planet with an extremely low albedo likely has a surface covered in a material that absorbs light incredibly well. One possibility is that these planets are coated in a thick layer of black carbon, similar to what we see on some asteroids in our solar system. Another possibility is that their atmospheres contain high concentrations of volatile compounds that absorb light across a broad spectrum. If we could somehow land a probe on one of these planets, what would we see? Imagine standing on the surface of a world where no light is reflected. The sky above would be an endless void, darker than anything we experience on Earth. Even if the planet had a nearby star, it might be completely invisible from the surface, as the atmosphere could absorb all incoming light before it reaches the ground. It would be a world of total darkness, where the only way to navigate would be through non-visual means, perhaps by feeling temperature differences or detecting electromagnetic fields. The question of life on these planets is another fascinating mystery. On Earth, almost all known life forms rely on sunlight in some way. But we do have examples of organisms that survive without it. Deep-sea creatures near hydrothermal vents use chemosynthesis instead of photosynthesis, deriving energy from chemicals rather than light. Could similar life forms exist on low-albedo exoplanets? If these worlds have active geology, volcanic activity, or internal heat sources, they might have deep underground ecosystems that thrive in complete darkness. And then there's the question of whether these planets could support intelligent life. If an alien civilization evolved on a planet that never saw light, how would they perceive their surroundings? Would they develop senses entirely different from our own? Perhaps they would be highly attuned to temperature changes, pressure variations, or even subtle shifts in gravitational fields. If they never developed vision as we understand it, their concept of the universe would be completely different from ours. They might not even have a concept of light or color, experiencing reality in ways we can't even begin to imagine. But the biggest and most unsettling possibility is that some of these low-albedo exoplanets might not be naturally occurring at all. If an advanced civilization wanted to hide, they might deliberately engineer their planet's surface or atmosphere to absorb all incoming light, making them invisible to prying eyes. This concept has led to the idea of stealth planets, worlds that are deliberately concealed from detection. The motives behind such an effort could vary. Perhaps these civilizations are avoiding potential threats, or maybe they have no interest in making contact with the wider universe. If we think about our own technological trajectory, humanity is already experimenting with materials that absorb nearly all light, such as vantablack. If a more advanced civilization has perfected this technology on a planetary scale, their worlds could be effectively invisible. Some have even speculated that low-albedo planets could be used as massive energy collectors, harvesting light from nearby stars and converting it into usable power without emitting any detectable radiation. This leads to an even wilder idea. What if some of these planets aren't just absorbing light, but actively using it in ways we don't understand? If a civilization had the ability to manipulate light at a fundamental level, they might have developed technology that bends or redirects light rather than simply absorbing it. This could allow them to remain completely hidden, even when they are right in front of us. The search for these dark worlds is still in its early stages, but every discovery brings us closer to understanding the hidden universe. As new telescopes and observational techniques are developed, we may begin to uncover more of these mysterious planets. Some will likely be natural formations, with unique chemical compositions that make them appear dark. Others may challenge our understanding of planetary science and force us to reconsider what is possible. The more we learn, the more questions arise. Are these planets common, or are they rare anomalies? Do they exist in specific regions of the galaxy, or are they scattered randomly? And most importantly, what secrets do they hold? The universe is vast, and if we've learned anything from the search for exoplanets, it's that reality is often far stranger than we ever imagined. Low-albedo exoplanets are just one of many mysteries waiting to be uncovered. The more we explore, the more we realize how little we truly know. Perhaps, somewhere in the depths of space, there's a world so dark that it has never been seen, a planet that holds answers to questions we haven't even thought to ask yet. The search continues, and with each new discovery, we get one step closer to unraveling the hidden secrets of the cosmos. The implications of low-albedo exoplanets extend beyond just their detection. They challenge our very understanding of planetary formation and evolution. Most planets we know of have some level of reflectivity, influenced by clouds, ice, or rocky surfaces. But if a planet absorbs almost all light, then something fundamental must be different. Are these planets born this way? Or do they undergo some process that darkens them over time? This is a question that scientists are still trying to answer. One possibility is that low-albedo exoplanets form in regions of space rich in dark materials, compounds that naturally absorb light rather than reflecting it. Some carbon-rich planets in our own solar system, like certain asteroids, have this property. If a planet forms in an environment dominated by such materials, its surface could naturally be coated in a substance that makes it nearly invisible. However, this doesn't explain why some gas giants, like Trace 2b, exhibit such extreme darkness despite their gaseous compositions. This leads to another theory. Perhaps some planets start off reflective but lose their brightness over time due to chemical reactions in their atmospheres. If a planet is close to its star, intense radiation could break down reflective molecules, leaving behind only those that absorb light. This could explain why some of the darkest exoplanets discovered so far are hot Jupiters, massive gas giants that orbit extremely close to their stars. Their atmospheres are constantly bombarded with radiation, which could alter their chemical compositions and make them appear darker. But what about planets that are far from their stars, yet still have low albedos? The farther a planet is from its star, the less likely it is to be exposed to intense radiation that would strip away reflective materials. This suggests that there may be other processes at work, such as geological activity. If a planet experiences widespread volcanic eruptions, it could be covered in fresh layers of basaltic rock, which is known to absorb light. Similarly, if a planet has vast oceans of hydrocarbons, like Saturn's moon Titan, it could appear almost entirely black when viewed from space. Then there's the question of whether these planets might have artificial origins. If an advanced civilization wanted to construct a megastructure designed to absorb as much light as possible, what would it look like? Some theorists have speculated that low-albedo exoplanets could be Dyson spheres in disguise, structures built around stars to capture all of their energy output. While most Dyson sphere models assume a reflective shell, a civilization could instead opt for a structure that absorbs rather than reflects, making it nearly impossible to detect from a distance. Even without going as far as Dyson spheres, it's possible that a technologically advanced species might deliberately engineer their planet to be less visible. If we assume that alien civilizations are aware of each other's existence, and that some might be hostile, the ability to disappear into the darkness of space could be a major strategic advantage. A planet that doesn't reflect light wouldn't show up easily on optical surveys, making it harder for other civilizations to detect and target. Another possibility is that these planets are not naturally dark, but instead have atmospheres filled with exotic particles that absorb nearly all light. On Earth, certain atmospheric conditions can make the sky appear red, orange, or even black under extreme circumstances. What if a planet's atmosphere was composed of unknown compounds that absorb not only visible light but also infrared, ultraviolet, and other wavelengths? Such a planet would be effectively invisible to most forms of detection, making it one of the hardest types of celestial bodies to study. Some scientists have proposed that low-albedo exoplanets could be rogue planets, worlds that have been ejected from their home systems and now drift through space without a star. If a planet has no nearby light source, it wouldn't reflect any light to begin with, making it nearly impossible to detect. These rogue planets could be common throughout the galaxy, yet we might only be aware of a fraction of them because of how difficult they are to find. If we ever manage to explore one of these planets up close, what might we discover? The possibilities are endless. If a planet has an atmosphere thick enough to absorb all light, it could be a world of perpetual darkness, where nothing is ever truly visible. Even standing on the surface, an observer might see nothing but blackness in all directions. This raises questions about how life, if it exists, would adapt to such an environment. On Earth, life has evolved to take advantage of light in countless ways. Plants use photosynthesis, animals develop eyesight, and even deep-sea creatures rely on bioluminescence. But in a world without light, life would have to function entirely differently. Organisms might evolve to sense their surroundings through touch, temperature, or even echolocation. They could be highly sensitive to electromagnetic fields or possess other senses that are beyond human comprehension. Intelligent life on such a planet would develop in an entirely different way from us. Without the concept of light or color, their understanding of the universe would be fundamentally different. Their technology, art, and even language could be shaped by their dark environment. Would they even have a concept of visibility? Or would their world be defined by other forms of perception? The implications of low-albedo exoplanets stretch far beyond their physical properties. They force us to reconsider everything we assume about planetary science, detection methods, and even the search for extraterrestrial life. The universe may be filled with planets that we simply cannot see, hidden just out of reach, waiting to be discovered. With advancing technology, we may soon develop better ways to detect these dark worlds. The James Webb Space Telescope, along with future missions, will provide more insights into these mysterious planets. But for now, they remain one of the greatest enigmas of the cosmos, a reminder that the universe is still full of secrets waiting to be uncovered. These low-albedo exoplanets challenge not just our ability to detect them but also our ability to understand them. The existence of planets that absorb almost all light means we must rethink the way we search for planets in the first place. Most exoplanets are detected using the transit method, where a planet passes in front of its star and temporarily blocks some of the light. But if a planet absorbs nearly all light and has an atmosphere that doesn't scatter it, the dip in brightness might be so subtle that we miss it entirely. This raises an interesting question. How many planets have we failed to detect simply because they are too dark? If there are entire worlds out there that are practically invisible, then our estimates of the number of exoplanets in the galaxy could be drastically underestimated. It's possible that some planetary systems we believe to be empty actually contain multiple dark planets, lurking just beyond the reach of our current technology. The next major challenge is figuring out what these planets are made of. Scientists can usually infer a planet's composition based on the light it reflects, but low-albedo exoplanets don't give us that luxury. Instead, we must rely on indirect methods, such as analyzing their gravitational influence on nearby objects, or studying the limited amount of heat they emit. This makes it incredibly difficult to determine whether these planets are covered in exotic minerals, thick layers of hydrocarbons, or even entirely unknown substances. One theory suggests that some low-albedo exoplanets could be covered in a dense, soot-like material. This could be the result of incomplete combustion of organic compounds in the atmosphere, similar to the way smoke particles absorb light on Earth. If a planet's atmosphere is rich in hydrocarbons and exposed to intense radiation, chemical reactions could produce a thick haze that blocks almost all light from escaping. This is similar to what happens on Saturn's moon Titan, though on an even more extreme scale. Another possibility is that these planets have metallic or carbon-rich surfaces that naturally absorb most wavelengths of light. Some planets might be covered in vast plains of iron or graphite, materials that are naturally dark. In some extreme cases, entire planets could be composed mostly of pure carbon, forming a carbon planet, with a surface of blackened diamond or graphite. If such a world exists, it would be one of the strangest planets in the universe, an entire planet made of carbon-based materials, yet appearing almost completely invisible from a distance. If a planet is a gas giant with an unusually dark atmosphere, then its darkness might be caused by high-altitude clouds made of exotic compounds. Some researchers suggest that alkali metals, such as sodium and potassium, could be responsible for absorbing large amounts of light. These elements are known to create dark, hazy atmospheres when present in high concentrations, potentially explaining why some hot Jupiters appear so dark. The most extreme example of a known low-albedo exoplanet is Trace 2b, which reflects less than 1% of the light that hits it. To put that in perspective, it's darker than coal, darker than fresh asphalt, and darker than the blackest paint on Earth. If you were floating above this planet, you wouldn't be able to see its surface at all. It would be a pitch-black void against the backdrop of space, with only a faint red glow from its heated atmosphere. But why would a planet evolve to be this dark? Some scientists believe that low-albedo exoplanets could be a natural result of planetary evolution, shaped by millions of years of exposure to extreme radiation. Others argue that their darkness could be the result of catastrophic events, massive asteroid impacts, volcanic eruptions, or even interactions with other planets that stripped away their reflective layers. And then there are the more speculative ideas. Could some of these planets be artificial? If an advanced civilization wanted to avoid detection, a dark, non-reflective planet would be the perfect hiding spot. Some researchers have even proposed the idea of stealth planets, worlds that have been deliberately engineered to absorb all incoming light, making them virtually undetectable. This might sound like science fiction, but consider how difficult it already is to detect planets beyond our solar system. Even with our most advanced telescopes, we struggle to see most exoplanets directly. If a civilization had the ability to manipulate a planet's atmosphere or surface composition, they could easily render it invisible to our current detection methods. If low-albedo exoplanets harbor life, it would likely be adapted to complete darkness. On Earth, we find life in some of the most extreme environments imaginable: deep-sea hydrothermal vents, underground caves, and even inside rocks. If life can thrive in those conditions, then it's entirely possible that organisms on a dark planet would evolve to navigate their world without relying on sight. Instead of vision, they might use echolocation, electromagnetic sensitivity, or even an entirely unknown sense. Some deep-sea creatures on Earth can detect electric fields generated by other animals, allowing them to see in complete darkness. If a species evolved on a low-albedo planet, they might develop an even more sophisticated way of sensing their surroundings, one that we can't even imagine. And what if intelligent life existed on one of these planets? A civilization that evolved in a world without light would have no concept of sight, color, or even day and night. Their entire understanding of the universe would be shaped by their sensory experiences, which might be completely different from ours. Their technology would be built around sound, touch, and other forms of perception that we can't fully grasp. This could make communication with such a civilization incredibly difficult. Most of our methods for detecting alien life, radio signals, optical telescopes, and even laser-based communication, rely on the assumption that other species perceive the universe in similar ways. But if an alien civilization evolved in total darkness, they might have no use for light-based communication at all. They might rely on entirely different forms of signaling, which we haven't even thought to look for. If we ever do manage to visit one of these planets, the experience would be unlike anything else. Imagine landing on a world where the ground is as dark as the sky, where everything is invisible unless you physically touch it. Your flashlight wouldn't reveal anything, because there would be nothing for the light to reflect off of. Even standing on the surface, you might feel like you were floating in an infinite void. But what if there were creatures lurking in that darkness? If an ecosystem existed on such a planet, it would be the most alien form of life we've ever encountered. Without eyes or any need for vision, they might communicate through vibrations, temperature changes, or even chemical signals. Their bodies could be adapted to a world without light in ways that completely defy our expectations. The discovery of low-albedo exoplanets forces us to rethink everything we assume about the universe. They remind us that there are still countless mysteries waiting to be uncovered, and that the cosmos is far stranger than we ever imagined. With new telescopes and detection methods on the horizon, we may soon get a better understanding of these hidden worlds. But for now, they remain one of the greatest enigmas of modern astronomy, a reminder that in the vastness of space, there are still places where even light itself dares not shine. The implications of low-albedo exoplanets extend far beyond just their detection. These planets challenge fundamental assumptions about planetary formation, climate dynamics, and even the very physics of light interaction with matter in extreme conditions. If a planet absorbs nearly all incoming radiation, it must have an energy balance unlike anything we've seen before. The heat it absorbs has to go somewhere, and if it doesn't reflect light, it must be re-emitted as infrared radiation. This means that even though these planets appear pitch black to the human eye, they might glow faintly in thermal wavelengths. Infrared observations have already revealed strange thermal patterns on some of these planets, hinting at bizarre atmospheric dynamics. Trace 2b, for example, despite being nearly black, still emits a faint red glow due to its extreme surface temperature. This suggests that even though the planet is absorbing nearly all visible light, its surface or atmosphere still radiates heat. But here's where things get even stranger. Some low-albedo exoplanets don't radiate as much infrared light as expected. That means they might be trapping heat in ways we don't fully understand. One possibility is that these planets have extremely thick atmospheres that act as insulators, trapping heat like a planetary-scale thermos. The composition of such an atmosphere would need to be dominated by heavy greenhouse gases, perhaps carbon dioxide, methane, or even more exotic compounds not found in our solar system. If the heat gets trapped efficiently enough, the planet's interior could reach temperatures far beyond what we would expect for a planet of its size and distance from its star. In extreme cases, this could lead to runaway greenhouse effects or superheated interiors that keep the planet molten for billions of years. Another theory suggests that these planets might have an unusual way of redistributing heat. On Earth, our atmosphere and ocean currents help balance the temperature between the equator and poles, but on some exoplanets, this process might be taken to the extreme. If a planet has powerful jet streams or high-speed winds, the heat absorbed from its star might be rapidly transported across the entire planet. This could create a situation where there are no distinct hot or cold zones, just a uniform, superheated world covered in an ever-moving, turbulent atmosphere. But what if these planets are even stranger than that? Some researchers have speculated that low-albedo exoplanets might have exotic forms of matter on their surface, materials that interact with light in ways we can't yet explain. There's a possibility that some of these planets could be covered in a substance that absorbs light and converts it into other forms of energy almost instantly. Imagine a planet coated in a material that behaves like a perfect black hole for visible light, but instead of collapsing matter into a singularity, it simply dissipates energy in some unknown way. Could these materials be natural, or could they be artificial? That's a question that leads us into the realm of speculative but fascinating ideas. What if these dark exoplanets aren't naturally occurring at all, but instead are remnants of some ancient, advanced civilization? If a civilization had technology far beyond ours, they might have found a way to manipulate the surface of a planet to make it appear invisible from a distance. Perhaps they developed a way to create large-scale cloaking devices that absorb all incoming light, preventing detection from prying eyes across the galaxy. This might sound like something out of science fiction, but it's not entirely implausible. We already have materials on Earth, like carbon nanotubes and vantablack, that absorb nearly all visible light. A sufficiently advanced civilization could theoretically develop a material that covers entire planets, rendering them invisible to our telescopes. If such planets exist, they could be hiding in plain sight, right in our own galaxy, undetectable by any conventional means. And if they were artificial, what would their purpose be? Would they be used as hiding spots, stealth planets designed to avoid detection? Could they be massive energy collectors, absorbing all incoming radiation for some unknown technological purpose? Or could they be relics of an ancient war, planets deliberately engineered to be invisible weapons, drifting silently through space, waiting for a signal that will never come? Even if we assume these planets are entirely natural, they still present deep mysteries. If their surfaces are covered in exotic materials, where did those materials come from? Did these planets form in an environment vastly different from our own solar system? Were they bombarded with darkened debris from ancient cosmic collisions? Or did they originate as bright, reflective worlds that later underwent some unknown transformation that turned them into black voids? Some astronomers have proposed that low-albedo exoplanets might be a missing link in our understanding of planetary evolution. Perhaps all planets go through a phase where they are dark, absorbing more light than they reflect. Maybe Earth itself was once covered in dark, light-absorbing minerals before plate tectonics and atmospheric changes altered its surface. If that's the case, then studying these planets could reveal secrets about our own past, clues to how our world transformed from a potential dark exoplanet into the life-filled blue marble we see today. The real breakthrough in studying low-albedo exoplanets might come from upcoming space telescopes. NASA's James Webb Space Telescope has already started scanning exoplanets in unprecedented detail, and future missions could take this even further. New technologies might allow us to analyze their atmospheres with more precision, detecting specific chemical signatures that give us hints about their composition. If we can figure out what makes these planets so dark, we might unlock new insights into chemistry, physics, and even astrobiology. What if these planets turn out to be the best places to look for alien life? We often assume that planets with high reflectivity, like Earth, are the most likely to harbor life because they reflect sunlight in a way that supports stable temperatures. But what if life on some planets thrives precisely because they are dark? If a planet absorbs nearly all light, it might retain heat more efficiently, allowing for stable environments even in otherwise inhospitable regions of space. Consider rogue planets, worlds that drift freely through space without orbiting a star. If a rogue planet had a surface similar to a low-albedo exoplanet, it might absorb the faint radiation of distant stars, retaining just enough heat to sustain a hidden biosphere. Deep under its surface, beneath layers of heat-trapping materials, an entire alien ecosystem could be thriving, unknown to the rest of the universe. If such a planet existed, it would be one of the most difficult to detect, but also one of the most profound discoveries in human history. It would prove that life doesn't need a sun, that life doesn't need a reflective, blue and green world like Earth. It would show us that life can exist in places we never even thought to look, in the void, in the darkness, on planets that swallow light itself. For now, low-albedo exoplanets remain one of the most intriguing and mysterious categories of planets we've discovered. They challenge our understanding of physics, they push the limits of our detection methods, and they open the door to new possibilities about the nature of planets and life beyond Earth. As our technology improves, we may soon find answers to the questions they pose, or we may uncover even deeper mysteries. But one thing is certain, the universe is far stranger than we ever imagined. And somewhere out there, in the depths of space, are planets so dark that even light itself cannot escape their grasp. Low-albedo exoplanets are among the most perplexing celestial objects in the universe, absorbing nearly all light that falls upon them. While we've identified a few such planets, like Trace 2b, the true nature of these dark worlds remains an enigma. Why do some exoplanets reflect almost nothing? What mechanisms allow them to remain so dark, and what hidden processes might be at work beneath their pitch-black surfaces? One of the primary reasons a planet might have a low albedo is its atmospheric composition. Many of the known dark exoplanets are gas giants, meaning they don't have solid surfaces like Earth or Mars. Instead, they have thick atmospheres composed of gases such as hydrogen, helium, and possibly more complex molecules. If the atmosphere lacks reflective clouds, such as the bright ammonia clouds seen on Jupiter, then there's little to scatter incoming light back into space. Instead, light is absorbed and either re-emitted as heat or trapped within deep atmospheric layers. Some scientists believe that the darkness of these exoplanets may be due to high concentrations of volatile compounds like sodium and potassium in their atmospheres. These elements are known to absorb large portions of the visible spectrum, preventing light from reflecting off the planet's atmosphere. If such compounds are abundant in an exoplanet's upper atmosphere, they could make the planet appear nearly black when viewed from afar. But why do some planets retain these light-absorbing compounds while others do not? One possible explanation is temperature. Many low-albedo exoplanets orbit extremely close to their host stars, making them hot Jupiters, gas giants that have been superheated by intense stellar radiation. At such extreme temperatures, many of the substances that would normally form reflective clouds, such as water vapor, ammonia, or methane, are broken down into simpler molecules. Instead of forming bright clouds, these planets develop thick, heat-trapping atmospheres filled with metal vapors, carbon compounds, and other dark materials that absorb most incoming light. However, there are low-albedo planets that don't fit this profile. Some are located farther from their stars, where they should be cool enough to retain bright, reflective clouds. And yet, they remain dark. This suggests that there might be other processes at work, processes that go beyond simple atmospheric composition and temperature. One possibility is that these planets have unusual surface materials that absorb most of the light that reaches them. If a low-albedo exoplanet has a solid or semi-solid surface beneath a thin atmosphere, that surface could be covered in dark, light-absorbing minerals. On Earth, we have substances like basalt and volcanic rock, which can appear very dark. But exoplanets might have even more exotic materials, perhaps surfaces rich in metals, carbon-based compounds, or even substances we haven't yet discovered. Some researchers have speculated that carbon itself could play a major role in the darkness of these planets. In our solar system, objects like Saturn's moon Iapetus have a striking difference in reflectivity between their bright and dark sides. The dark material on Iapetus is thought to be composed of organic compounds or carbon-based dust, possibly from meteor impacts or space debris. If a similar process were at work on exoplanets, they could accumulate thick layers of carbon-based material, making them appear blacker than coal. But what if these planets aren't just covered in dark materials? What if they're generating them? Some scientists have theorized that extreme heat and pressure on certain exoplanets might create conditions where carbon is transformed into exotic forms, such as graphene or even microscopic black carbon dust. These substances are excellent at absorbing light, meaning that if they were present in a planet's upper atmosphere, they could create a nearly perfect light-absorbing layer. Another theory suggests that these planets might have an unusual way of dispersing light rather than reflecting it. Instead of scattering light back into space, their atmospheres could trap and redirect it in unpredictable ways. This would make them appear darker than they actually are because much of the incoming light would be absorbed and then re-radiated as heat rather than being reflected back in a way that our telescopes can detect. But could there be even stranger explanations? Some have proposed that certain low-albedo exoplanets might not be naturally occurring at all. If an advanced civilization were to build massive artificial structures on the surface of a planet or in its atmosphere, those structures could be designed to absorb nearly all light, making the planet appear unnaturally dark. This idea is speculative, but it's not entirely out of the realm of possibility. Imagine a civilization that wanted to remain hidden. If they developed materials capable of absorbing nearly all incoming radiation, they could effectively make their planet invisible to distant observers. In some ways, this would be the ultimate form of stealth, an entire world that absorbs light so efficiently that it leaves no trace of its presence. Could some of the low-albedo exoplanets we've detected be artificial? If so, how would we ever know? Even without invoking artificial structures, the idea of alien life on these dark planets is an intriguing one. Could life evolve on a world where nearly all visible light is absorbed rather than reflected? On Earth, many organisms have adapted to life in extreme environments. Deep-sea creatures survive in near-total darkness, and certain bacteria thrive in high-temperature, high-pressure environments. If a low-albedo exoplanet had a stable atmosphere and the right chemical conditions, it's possible that life could develop in ways we've never imagined. One possibility is that such planets could harbor lifeforms that rely on infrared radiation rather than visible light. Instead of using photosynthesis to capture energy from starlight, these organisms might absorb and utilize heat energy from the planet's own surface or atmosphere. This would be an entirely different kind of biology, one that doesn't depend on the kind of light we see but instead operates in wavelengths invisible to the human eye. Another possibility is that these planets might have subsurface oceans or underground ecosystems. If a low-albedo exoplanet is absorbing vast amounts of heat from its star, that heat might be trapped beneath the surface, creating warm environments where liquid water could exist. If life had evolved there, it might be hidden beneath layers of dark, heat-absorbing material, making it even harder to detect. But the mystery of these planets isn't just about whether they could support life. It's also about what they tell us about the nature of planetary formation and evolution. If low-albedo exoplanets are common, it could mean that there are entire categories of planets we've never even considered before. Planets that don't fit into the traditional molds of rocky Earth-like worlds or gas giants like Jupiter. Instead, they might represent a missing link in our understanding of how planetary systems evolve. For now, we are only beginning to scratch the surface of what these dark worlds might be. Future telescopes and observation techniques will help us probe deeper into their mysteries, analyzing their atmospheres, temperatures, and compositions in more detail. The more we learn, the more we may realize that our assumptions about planets, what they should look like, how they should behave, might be completely wrong. If there's one thing that low-albedo exoplanets have taught us, it's that the universe is full of surprises. These dark worlds defy expectations, challenge our models, and hint at possibilities we've never even dreamed of. Whether they are home to exotic materials, extreme atmospheres, or even alien civilizations, one thing is certain: they are among the most fascinating and mysterious planets in the cosmos. And as we continue our search, who knows what other dark secrets the universe might be hiding? The mystery of low-albedo exoplanets is far from solved. In fact, with each new discovery, more questions arise. One of the biggest challenges in understanding these planets is the limitation of our current observational technology. When we detect an exoplanet, we usually rely on indirect methods, such as measuring how much light it blocks when it passes in front of its star, the transit method, or observing how its gravity affects the motion of its star, the radial velocity method. But these techniques don't directly show us what the planet looks like. For low-albedo exoplanets, this is a significant problem because their darkness makes them nearly invisible. Unlike highly reflective planets, which can be seen more easily in direct imaging, dark exoplanets blend into the blackness of space. This means that the details of their atmospheres and surfaces remain largely unknown. However, new technologies, like the James Webb Space Telescope, JWST, and future high-contrast imaging techniques, are beginning to change that. JWST, for example, has the ability to analyze the light that filters through a planet's atmosphere as it transits its star. This process, called transmission spectroscopy, allows scientists to determine what gases are present. If a low-albedo exoplanet has an atmosphere full of light-absorbing compounds, JWST can detect their chemical signatures. This could help confirm whether these planets are dark due to their atmospheric composition, surface material, or something even stranger. But what happens when we come across a planet that is darker than anything our models predict? Some exoplanets, like Trace 2b, absorb nearly all light, reflecting less than 1%, essentially appearing as a black hole in the sky. But could there be planets that absorb even more? Could there be exoplanets that are so dark they are functionally invisible? This leads to one of the more speculative, yet fascinating, ideas in astrophysics: the possibility of cloaked exoplanets. Imagine a planet that is naturally or artificially designed to absorb nearly all light and radiation, making it undetectable through normal means. In theory, if an advanced civilization wanted to hide an entire planet, they could create a surface or atmosphere that absorbs all electromagnetic waves, leaving no signal behind. While this is purely hypothetical, it raises an intriguing question: have we already missed planets that are perfectly hidden in plain sight? Even if these planets aren't deliberately hidden, the idea of near-invisible worlds changes our understanding of planetary classification. Most of the planets we know are classified based on their size, composition, and reflectivity. But what if low-albedo exoplanets represent an entirely different type of celestial object, one that doesn't fit neatly into our current models? One of the most puzzling aspects of these planets is how they maintain their darkness over time. In theory, planets should undergo geological and atmospheric changes, just like Earth. Over millions of years, volcanic activity, asteroid impacts, and even interactions with their stars should alter their surfaces. If a planet starts out dark, why does it stay that way? Could there be self-sustaining processes that continuously regenerate light-absorbing materials? One possibility is the constant deposition of dark aerosols from volcanic activity. On Earth, massive volcanic eruptions can release ash and sulfur compounds that block sunlight and temporarily cool the planet. If a low-albedo exoplanet has continuous volcanic activity, it could be constantly replenishing its atmosphere with heat-absorbing particles, keeping it dark indefinitely. Another possibility is that these planets are covered in materials that chemically react with their environment in a way that maintains their darkness. For example, some substances darken when exposed to radiation, similar to how some minerals change color when exposed to sunlight. If a planet is bathed in intense stellar radiation, its surface or atmosphere might develop self-reinforcing dark layers that make it appear permanently black. Yet another idea is that these planets could be covered in exotic, light-absorbing liquids or oceans. On Earth, bodies of water reflect some sunlight, but if a planet had oceans filled with pitch-black liquids, perhaps hydrocarbons, metallic fluids, or unknown substances, they could create a world that appears uniformly dark from space. One of the most fascinating aspects of low-albedo exoplanets is how they challenge our understanding of habitability. We often associate life with bright, reflective planets because they seem more Earth-like. However, darkness doesn't necessarily mean lifelessness. If anything, extreme environments on Earth have proven that life can survive in the most unexpected places. For example, deep in our oceans, there are ecosystems that rely on hydrothermal vents for energy rather than sunlight. These vents release heat and chemicals that sustain entire food chains, with organisms that don't need photosynthesis at all. If a low-albedo exoplanet has a thick atmosphere that absorbs most light but retains enough heat, similar processes could take place in its clouds or oceans. But what if intelligent life existed on one of these planets? How would it develop in a world where visible light is nearly absent? Would their eyes be adapted to infrared vision? Would they use heat as their primary way of sensing the world? And if they evolved advanced technology, would their entire civilization operate in a spectrum of light that is invisible to us? The more we think about low-albedo exoplanets, the more they force us to reconsider what we think we know about planetary science, habitability, and even the search for extraterrestrial intelligence. If intelligent life evolved on such a planet, would they even recognize our form of communication? Our radio signals, based on wavelengths that reflect well in our environment, might be completely undetectable to them. They might use heat signatures or electromagnetic fields instead, things we're not actively looking for. This means that some of the most mysterious planets in the universe might not just be strange in terms of their appearance, but also in terms of the way they interact with the cosmos. If a civilization developed on a world where nearly all light was absorbed, would they even think to look for signals in visible wavelengths? Would they even know that the rest of the universe exists in the way we see it? As our telescopes improve, we may begin to detect more of these dark worlds. And with each new discovery, we may inch closer to answering one of the most fundamental questions in astronomy: what else is out there? Low-albedo exoplanets are a reminder that the universe is not just full of light, but also full of darkness, and within that darkness, mysteries are waiting to be uncovered. Low-albedo exoplanets are not just rare cosmic oddities. They may represent an entire category of planets that defy our current expectations. As technology advances, we are starting to detect more of these dark worlds, but their true nature remains a mystery. Are they simply covered in light-absorbing materials, or is there something deeper at play? Could they be home to exotic forms of chemistry, unknown atmospheric processes, or even life forms that thrive in darkness? One of the most perplexing questions about these planets is how they remain so dark over time. Planets, like stars, undergo changes throughout their lifetimes. They experience geological activity, atmospheric evolution, and bombardment from cosmic debris. Over millions or even billions of years, these processes should alter their appearance. Yet, low-albedo exoplanets seem to maintain their near-black surfaces. Some scientists believe that the answer lies in the materials that make up these planets. Certain compounds, like titanium dioxide, can absorb vast amounts of light. If these planets are covered in reflective absorbing minerals, their darkness could be a natural consequence of their composition. But what's strange is that some of these planets appear to be darker than even the blackest known substances. This raises the question, could they contain materials that we have never encountered before? Beyond surface materials, another explanation could be extreme atmospheric conditions. Some exoplanets have thick, hazy atmospheres filled with soot-like particles. These particles, which are common in planets with high temperatures, can trap light and prevent it from escaping. This creates a cycle in which the planet continues absorbing radiation, making it appear darker. But what if some of these planets have atmospheres unlike anything we've seen before? What if they contain chemical reactions that produce completely unknown forms of dark aerosols? Some scientists have speculated that low-albedo exoplanets might have atmospheres rich in exotic carbon-based molecules, absorbing nearly all light that touches them. If true, these planets could be like cosmic sponges, soaking up energy without reflecting it back into space. This raises another fascinating possibility. If these planets absorb more energy than they release, where does all that energy go? Does it get trapped beneath the surface? Does it fuel internal geological activity? Or could it be supporting entirely new forms of alien ecosystems? The idea of life on low-albedo exoplanets is one of the most intriguing aspects of this mystery. We typically think of life as being dependent on sunlight. After all, Earth's entire biosphere is built on the foundation of photosynthesis. But what if life on these planets doesn't rely on light at all? On Earth, we've discovered extremophiles, organisms that thrive in complete darkness, deep under the ocean or inside caves. Some bacteria and archaea can survive without sunlight by using chemical energy from minerals. If a low-albedo exoplanet has a dense, heat-trapping atmosphere, it might have similar conditions, creating an environment where life thrives in eternal night. In such a world, creatures wouldn't need eyes that detect visible light. Instead, they might rely on infrared vision, heat sensitivity, or even electromagnetic field detection to navigate their surroundings. Their biology could be adapted to absorb and process the faintest traces of energy, using chemical reactions unknown to us. But what if life on these planets isn't just microbial? What if entire ecosystems exist, teeming with creatures adapted to darkness? Imagine alien forests where bioluminescent plants glow faintly in the infrared spectrum. Imagine predators that hunt using heat detection, preying on organisms that have developed camouflage not in terms of color, but in terms of temperature. This concept also raises a bigger question. If intelligent life evolved on one of these planets, how would they perceive the universe? Would they even know that stars exist? Would they think of light in the same way we do, or would their entire understanding of physics and communication be built around heat, pressure, or magnetism? If an advanced civilization developed on a world like this, their technology might be completely invisible to us. They wouldn't rely on radio signals or visible wavelengths. They might use thermal signals or even gravitational distortions to send messages. Could it be that we've been looking for extraterrestrial life in all the wrong ways? Could civilizations exist right now, undetectable because their entire existence operates outside our visible spectrum? Even if intelligent life doesn't exist on these planets, their extreme environments could teach us valuable lessons about physics, chemistry, and planetary evolution. By studying them, we might uncover new principles of how atmospheres interact with radiation, or even discover materials with properties we never thought possible. As our telescopes improve, we will undoubtedly detect more of these dark worlds. The James Webb Space Telescope is already capable of analyzing exoplanet atmospheres, and future missions, like the proposed LUVOIR and HabEx space telescopes, will take this even further. With direct imaging, we may one day see the first ever detailed image of a low-albedo exoplanet, revealing its true nature. But until then, these planets remain one of the greatest mysteries of space. Are they simple cosmic oddities, or do they hold the key to understanding new realms of physics and biology? Could they be hiding the most extreme forms of life in the universe? Or are they something even stranger, something beyond our current ability to comprehend? One thing is certain, the cosmos is filled with surprises, and low-albedo exoplanets are some of the most enigmatic objects we've ever encountered. As we continue searching, we may find that the darkest places in the universe hold the brightest secrets. If we truly want to understand low-albedo exoplanets, we need to rethink how we search for them. Most of our planet hunting techniques rely on detecting changes in brightness. When a planet passes in front of its star, it dims the light slightly. But what happens when a planet is so dark that it barely reflects any light at all? Could it be that entire populations of planets are hiding in the cosmos, completely invisible to our current methods? This question forces us to consider an unsettling possibility. What if low-albedo exoplanets are far more common than we think, but we simply lack the right tools to detect them? Imagine billions of planets orbiting distant stars, absorbing nearly all the light that touches them, remaining unseen despite being right in front of us. It's entirely possible that some of the closest exoplanets to Earth are nearly pitch black, making them invisible even to our most advanced telescopes. One way to counter this limitation is through infrared observation. Since these planets absorb so much light, they should emit heat signatures instead. A planet like Trace 2b, for example, isn't completely invisible. It radiates a faint glow due to its temperature. If we focus on searching for heat instead of reflected light, we might uncover countless more dark planets lurking in the void. This approach is already being used in some of our most advanced telescopes. The James Webb Space Telescope, JWST for example, is designed to detect infrared radiation, making it a powerful tool for studying low-albedo exoplanets. Instead of looking for reflected starlight, JWST can detect the faint heat signatures of these worlds, allowing us to analyze their atmospheres, temperatures, and even their potential for hosting life. But even with infrared detection, there's still a challenge. What if some of these planets are so cold that they emit almost no detectable heat? If a low-albedo exoplanet is far enough from its star, it might absorb energy but not radiate enough to be seen. These worlds could be drifting undetected in the darkness, invisible to both optical and infrared telescopes. This raises an even more chilling possibility. Some of these planets might not be orbiting stars at all. Enter the concept of rogue planets, worlds that have been ejected from their solar systems and now wander the galaxy alone, with no parent star to warm them. Many of these rogue planets could have extremely low albedos, making them nearly impossible to detect. If such a planet were to pass near our solar system, we might never know it was there until it was too late. The idea of an unseen, black planet drifting silently through space, potentially on a collision course with another system, is both fascinating and terrifying. But if these rogue low-albedo planets exist, could they also harbor life? At first glance, it seems impossible. Without a star, where would they get their energy? But some scientists have proposed that internal heat, generated by radioactive decay or gravitational compression, could keep a rogue planet warm enough for life to persist. If such a world had a thick enough atmosphere, it could trap heat like a cosmic thermos, maintaining stable conditions for millions or even billions of years. What's even more intriguing is that some of these planets might have subsurface oceans, hidden beneath thick layers of ice. On Earth, we've discovered entire ecosystems living in the deep ocean, completely cut off from sunlight, surviving off chemical reactions instead. If a rogue low-albedo planet had a similar environment, life could theoretically thrive in total darkness, using geothermal energy instead of sunlight. This raises a profound question. If life can exist on a pitch-black planet, with no access to starlight, what does that mean for the search for extraterrestrial life? We've always assumed that alien life would evolve on planets similar to Earth, with oceans, atmospheres, and a sun-like star providing energy. But what if we've been looking in the wrong places? What if the most common forms of life in the universe exist in total darkness, hidden beneath thick atmospheres or icy crusts, undetectable by our current methods? The more we study low-albedo exoplanets, the more we realize how little we truly know. These worlds challenge our assumptions about planetary formation, atmospheric chemistry, and even the very nature of life itself. Some scientists have even speculated that understanding these dark planets could help us unlock deeper secrets of physics, perhaps even new forms of matter or energy interactions that we have yet to discover. For now, these planets remain some of the most mysterious objects in the universe. But with each new technological breakthrough, we inch closer to solving their secrets. Maybe one day, we'll send a probe to one of these worlds, capturing the first ever close-up images of a planet so dark that it swallows light itself. And when we finally see what lies on its surface, we may find that the truth is even stranger than we ever imagined. If we do eventually send a probe to one of these low-albedo exoplanets, the mission would be unlike anything humanity has ever attempted. Unlike bright, reflective planets that can be observed from great distances, these worlds would appear as nothing more than voids against the backdrop of space. Navigating such an environment would be a monumental challenge. How do you land on a planet you can barely see? How do you explore a world where light simply vanishes? To solve this problem, scientists might design probes that rely entirely on non-visual detection methods. Instead of cameras, they could use infrared sensors, radar mapping, or even sonar-like systems to build a picture of the surface. These probes would essentially feel their way through the darkness, using heat signatures and gravitational mapping to navigate and analyze the terrain. But what would they find once they arrived? Would the surface be smooth, covered in light-absorbing dust, or would it be jagged and unstable? If these planets are as dark as we think, their surface materials must be made of substances with incredibly strong absorptive properties. Could these materials have practical applications for us? Could the very substance that makes these planets so dark be the key to developing the perfect light-absorbing materials for energy production, cloaking technology, or even advanced computing? One of the most valuable things we might discover is how these planets maintain their low albedo over time. On Earth, natural processes like erosion, weathering, and tectonic activity gradually change the surface appearance of a planet. Yet some of these exoplanets have remained dark for billions of years. What prevents their surfaces from becoming reflective over time? Is there a process we don't yet understand that constantly replenishes these light-absorbing materials? And what if we discover something even more shocking, evidence that these planets are not naturally dark at all, but instead have been artificially engineered? This is a hypothesis that, while speculative, has intrigued some scientists. If an advanced alien civilization wanted to hide its planet from detection, making it as dark as possible would be one way to do it. A civilization with advanced knowledge of nanotechnology or energy absorption could theoretically create a planetary-scale cloak, rendering their world almost completely invisible to external observers. While this idea might sound far-fetched, it's worth considering that some of the most bizarre phenomena in the universe have turned out to be real. Just a few decades ago, black holes were considered theoretical constructs, and today we've captured actual images of them. Dark matter remains one of the greatest mysteries in physics, yet it makes up most of the universe's mass. If there are alien civilizations out there, it's possible they've found ways to manipulate light and visibility in ways we can't yet comprehend. But even if these planets are entirely natural, they still hold secrets that could revolutionize our understanding of planetary science. By studying them, we might develop new models for planetary formation, atmospheric evolution, and even climate control. If we can determine what makes these planets absorb so much light, we might one day apply that knowledge to our own technology, perhaps creating ultra-efficient solar panels, new forms of energy storage, or even planetary-scale solutions for controlling temperature and radiation. The search for low-albedo exoplanets is only just beginning. As our telescopes become more advanced and our detection methods improve, we may find that these dark worlds are far more common than we ever imagined. They might not just be rare anomalies, but an entire class of planets that have remained hidden in plain sight. And if that's the case, the biggest question remains: what else is lurking in the darkness? What secrets do these black worlds hold? And when we finally unlock their mysteries, will we be prepared for what we find? If low-albedo exoplanets are far more common than we previously thought, it forces us to reconsider our entire perspective on planetary diversity in the universe. Up until now, our understanding of exoplanets has largely been shaped by what we can detect, bright planets, massive gas giants, or worlds with atmospheres that interact strongly with starlight. But what if the majority of planets in the universe are nearly invisible to us? What if the standard planetary model isn't the reflective, colorful worlds we often imagine, but rather planets so dark that they absorb nearly all incoming light? If that's the case, then our current exoplanet catalog could be incredibly biased. The thousands of exoplanets we've discovered so far might only represent a fraction of what's really out there. It would mean that the true planetary landscape of the universe is still almost completely unknown to us. Imagine a cosmos filled with billions, maybe trillions, of these pitch-black planets, silent, hidden, and scattered across the galaxy like cosmic ghosts. This also raises the question, how did these planets form in the first place? Are there specific conditions that lead to such extreme darkness, or are there multiple pathways to becoming a low-albedo world? Some scientists believe that high concentrations of volatile compounds, like certain hydrocarbons or exotic minerals, could be responsible for their light-absorbing properties. Others speculate that these planets might have formed in regions of space with unique chemical compositions, leading to surfaces rich in materials that naturally absorb light. One possibility is that these planets were once reflective but underwent massive chemical transformations. Over millions or billions of years, their atmospheres might have reacted with their surfaces, creating thick layers of soot-like compounds that block nearly all light. If so, these planets could serve as time capsules, preserving the chemical history of their solar systems in ways that more reflective planets do not. Studying them could give us insights into the early days of planet formation and the evolution of planetary atmospheres. But there's another, even more unsettling theory. What if some of these planets became dark due to catastrophic events? One possibility is that they were once habitable worlds that suffered massive asteroid impacts, volcanic eruptions, or even artificial destruction. If a planet were to experience an event that released massive amounts of carbon-based particles into its atmosphere and onto its surface, it could eventually become a near-total absorber of light. This idea leads to even more thought-provoking questions. If some of these planets were once habitable, could they still retain traces of their past life? What if their blackened surfaces are covering up ancient ruins, fossils, or biological remnants of civilizations long gone? If we could study these planets up close, we might uncover evidence of alien life, not in the form of active civilizations, but as relics buried beneath layers of carbon-rich dust and debris. Some astronomers have suggested that these planets could also be remnants of interstellar warfare. If advanced civilizations once existed and engaged in large-scale conflicts, could they have used weapons that altered the reflectivity of entire planets? Could some of these worlds be the burned-out husks of planets that were once thriving but were reduced to blackened wastelands by weapons or energy-based technology? While this remains pure speculation, it's a fascinating thought experiment that forces us to rethink the potential history of the universe. On a more practical level, studying low-albedo exoplanets might help us prepare for planetary-scale environmental challenges on Earth. If we can understand the processes that make these planets so dark, we might be able to apply that knowledge to mitigating climate change, controlling heat absorption, or even developing more efficient ways to harness solar energy. The materials that cover these planets could inspire new technological innovations, from ultra-dark coatings to energy-absorbing fabrics and beyond. Ultimately, low-albedo exoplanets challenge us to think beyond what we can easily see. They remind us that the universe is not just made up of the bright, the reflective, and the visible, but also the hidden, the mysterious, and the unknown. These planets force us to develop new ways of observing, new methods of understanding, and new questions about what might be lurking just beyond our current reach. As technology advances and our ability to detect these worlds improves, we may soon enter a new era of exoplanetary science, one where the darkest planets are no longer invisible, and the secrets they hold finally come to light. When that day comes, the discoveries we make could be some of the most important in human history. Because in the darkness, there is always something waiting to be found. If low-albedo exoplanets are as common as some scientists suspect, it could mean that a significant portion of the universe remains hidden simply because of how we search for planets. Traditional methods of detection, like the transit method, rely on changes in starlight when a planet passes in front of its host star. But if a planet absorbs nearly all incoming light, the contrast might be so faint that it becomes nearly impossible to detect with our current instruments. This means that entire planetary systems could be lurking in the darkness, evading our detection methods simply because of their low reflectivity. One of the biggest challenges in studying these planets is determining what their atmospheres are made of. If they absorb most of the light that hits them, it becomes incredibly difficult to analyze their atmospheric composition through spectroscopy, which relies on analyzing how light interacts with different gases. This limitation forces scientists to think creatively about alternative ways to study these worlds. Some researchers have proposed using gravitational microlensing, a technique that detects planets by observing how their gravity bends the light of a background star. Others suggest searching for heat signatures instead of reflected light, using infrared telescopes to detect the warmth emitted by these planets. One intriguing aspect of low-albedo exoplanets is their potential for extreme climates. Without reflectivity to bounce incoming radiation back into space, these planets could become incredibly hot if they are close to their stars. Their surfaces might be covered in molten rock or high-temperature carbon compounds, forming landscapes unlike anything seen in our solar system. On the other hand, if they are far from their stars, they could become some of the coldest planets in existence, with their dark surfaces trapping minimal heat and plunging them into temperatures near absolute zero. The atmospheric conditions on these planets could be just as extreme. If they have thick, dense atmospheres, the greenhouse effect could turn them into smothering, high-pressure worlds, similar to Venus but on an even larger scale. On the other hand, if they lack substantial atmospheres, their surfaces might be exposed directly to space, leading to wild temperature swings between their day and night sides. Some scientists believe that these planets could have atmospheres composed of exotic gases that interact with light in unusual ways, potentially giving rise to strange weather patterns or even entirely new forms of chemical processes that don't exist on Earth. One of the strangest possibilities is that some low-albedo exoplanets could have subsurface oceans or hidden biospheres. If a planet is dark due to a thick layer of organic material or carbon-based compounds, it might still have liquid water beneath its surface, shielded from the harsh radiation of space. This could create conditions where life, potentially microbial or even more complex, could exist in complete darkness, surviving off chemical energy rather than sunlight. If so, these planets could be among the most promising candidates for alien life, hidden away beneath light-absorbing crusts that make them nearly impossible to see. Another fascinating theory is that some low-albedo exoplanets might not be planets at all, but instead, enormous rogue objects, remnants of failed star systems, or even collapsed stellar cores. Some astronomers have suggested that certain dark exoplanets could actually be dark Jupiters, failed gas giants that never fully formed into stars and instead became cold, featureless spheres of gas and dust. Others speculate that some of these objects might be composed primarily of exotic materials, such as metallic hydrogen or ultra-dense carbon structures, making them some of the strangest celestial bodies in existence. The potential for artificial structures on these planets is also a topic of intense speculation. If an advanced civilization wanted to build megastructures designed to absorb light, it might create surfaces that are nearly perfect absorbers of radiation. Some researchers have even considered the possibility that low-albedo planets could be massive alien superstructures, designed to blend in with the blackness of space to avoid detection. While this idea remains speculative, it challenges us to consider whether some of these planets are truly natural formations or if something, or someone, has engineered them to be as dark as possible. As technology advances, our ability to study these planets will improve. Next-generation space telescopes, like the James Webb Space Telescope and its successors, will allow us to analyze planetary atmospheres in greater detail, potentially revealing the chemical compositions of even the darkest worlds. Future missions might also involve direct imaging of exoplanets, using new techniques like starshade technology, massive space-based shields that block out a star's light, making it easier to observe faint objects nearby. Eventually, if we develop the capability for interstellar travel, low-albedo exoplanets might become some of the first destinations for exploration. Their mysterious nature makes them prime targets for scientific investigation, and if they do harbor life, they could provide answers to one of humanity's biggest questions: are we alone in the universe? If we find even the faintest traces of biological activity on these planets, it could change everything we know about life's potential in the cosmos. For now, these dark worlds remain among the greatest mysteries in space. They are invisible sentinels, hiding just beyond our reach, challenging us to develop new ways of seeing, thinking, and exploring. As our understanding of the universe deepens, one thing is certain: what we cannot see might be just as important, if not more so, than what we can. If low-albedo exoplanets are far more abundant than we currently realize, then our understanding of planetary evolution may need to be completely rewritten. The conditions that lead to their extreme darkness could be far more common than initially expected, suggesting that entire classes of planets exist that we have never even accounted for. This realization would mean that the typical exoplanet may not be a bright, colorful world like those we often see in artistic renderings, but instead a pitch-black sphere drifting through space, absorbing nearly all light that touches it. The composition of these planets is one of the biggest unknowns. While some might be covered in light-absorbing soot, carbon, or exotic minerals, others could have completely alien surface materials that absorb light in ways we don't yet understand. Scientists have proposed several potential explanations for why these planets appear so dark. One theory is that their atmospheres contain high concentrations of complex organic molecules, which form thick, black clouds that trap almost all incoming light. Another possibility is that their surfaces are covered in tar-like hydrocarbons, similar to the substance found on Saturn's moon Titan, but on a much larger scale. Some of these planets may have lost their atmospheres entirely, leaving behind bare, carbon-coated surfaces that act as cosmic light traps. Others could have atmospheres so dense and full of opaque particles that they absorb nearly all starlight before it has a chance to reflect off the planet's surface. These conditions would create a world of perpetual darkness, where the only sources of light would come from internal heat or electrical storms raging in the atmosphere. One particularly strange possibility is that some low-albedo exoplanets might be covered in a material similar to vantablack, a human-made substance that absorbs over 99% of visible light. If a planet developed a natural equivalent of this material through unique geological or chemical processes, it could become so dark that it would be almost invisible to telescopes. The discovery of such a material in nature would be groundbreaking, as it could reveal entirely new forms of chemistry and physics at work on these planets. Another major question is whether these planets are simply natural formations or if their extreme darkness could be the result of artificial engineering. If an advanced civilization wanted to make a planet nearly undetectable, one of the most effective ways to do so would be to make it as black as possible. A dark planet would be much harder to spot with optical telescopes, and if it also absorbed heat efficiently, it might even be difficult to detect with infrared sensors. Could some of these worlds be artificially modified for stealth, designed to hide from outside observation? This idea raises even more unsettling possibilities. If intelligent life exists elsewhere in the universe, and if some civilizations have deliberately darkened their planets to avoid detection, what are they hiding from? Are they simply avoiding other civilizations? Or are they aware of some larger cosmic danger that we are yet to discover? The possibility that some low-albedo exoplanets could be the result of intelligent design, rather than just natural processes, adds a whole new layer of mystery to these already enigmatic worlds. Even if these planets are entirely natural, their existence still forces us to reconsider how we search for exoplanets. Since most of our detection methods rely on a planet's ability to reflect or block light, we may have already missed thousands, if not millions, of these dark worlds. If they are common, then our current estimates for the number of planets in the galaxy could be far too low. We might be vastly underestimating the true abundance of planetary systems, simply because the darkest planets are the hardest to see. One of the most exciting ways to study these planets in the future is through direct imaging. While current telescopes struggle to detect dark exoplanets, next-generation observatories, such as the upcoming Nancy Grace Roman Space Telescope, could help reveal their presence. Future missions could use coronagraphs, devices that block out the bright light of a star, making faint objects nearby easier to see. Another promising technique is starshade technology, where a spacecraft deploys a massive shield to block a star's light, allowing telescopes to see dimmer planets that would otherwise be drowned out by glare. If we ever send interstellar probes beyond our solar system, low-albedo exoplanets might be some of the most fascinating targets for exploration. A spacecraft equipped with advanced imaging and spectroscopic instruments could determine what these planets are really made of, how they formed, and whether they have any conditions that could support life. If we find biological markers, such as complex organic molecules, unusual atmospheric chemistry, or even direct evidence of microbial activity, it could completely redefine our understanding of where life can exist in the universe. Some researchers have even suggested that low-albedo exoplanets could play a role in future human expansion beyond Earth. If these planets have thick atmospheres or subsurface oceans, they might be able to sustain life under the right conditions. Colonizing such a planet would present unique challenges, such as the lack of natural light. But with the right technology, a human presence could potentially be established on even the darkest of worlds. As we continue to push the boundaries of astronomy, we may discover that these black planets are far more than just cosmic anomalies. They could hold the keys to understanding planetary formation, the distribution of life in the universe, and even the nature of advanced civilizations. For now, they remain one of the greatest mysteries of space, hidden in plain sight, waiting for us to uncover their secrets. If low-albedo exoplanets are more common than we think, they could significantly alter our understanding of planetary diversity in the universe. Astronomers have long believed that most planets should have some level of reflectivity, whether from cloud cover, icy surfaces, or atmospheric scattering. However, the discovery of numerous dark exoplanets challenges this assumption, suggesting that many worlds may be nearly invisible in conventional optical observations. This raises an even bigger question: how many of these dark planets are out there, and what does their existence tell us about planetary formation and evolution? One possible explanation for their darkness lies in the chemical makeup of their atmospheres. On Earth, we see a wide range of reflective surfaces, from bright white clouds to shimmering oceans, yet some materials naturally absorb light with incredible efficiency. If an exoplanet's atmosphere is rich in certain hydrocarbons, carbon compounds, or metallic vapors, it could act as a near-perfect light trap. A planet shrouded in thick layers of high-temperature clouds made of titanium oxide, vanadium oxide, or silicate dust could absorb nearly all the light that strikes it. Other planets may have surfaces coated in exotic materials that are naturally dark. For instance, some theories suggest that planets with high volcanic activity could be covered in large deposits of basaltic lava, which absorbs much more light than other types of rock. Others might have surfaces covered in ultra-thin layers of metals or carbon-based compounds, much like the soot that accumulates from combustion. If these substances dominate the surface, the planet would appear almost entirely black when viewed from space. One of the most famous low-albedo exoplanets ever discovered is Trace 2b, a gas giant orbiting its star at an extremely close distance. This planet is darker than coal, reflecting less than 1% of the light that hits it. Scientists believe that its extreme darkness is due to the presence of gaseous alkali metals, such as sodium and potassium, in its atmosphere. These elements absorb visible light rather than reflecting it, making the planet nearly invisible. However, Trace 2b is still not completely black. It emits a faint red glow due to the intense heat it receives from its nearby star. This eerie phenomenon raises another question: could some of the darkest planets in the universe still be glowing with heat, hidden from our telescopes except in infrared wavelengths? Beyond their composition, the behavior of these dark exoplanets is another fascinating mystery. Some of them orbit their stars in extreme, unpredictable ways. Unlike Earth, which rotates on its axis and experiences day and night cycles, many of these planets are tidally locked, meaning that one side of the planet always faces the star while the other remains in eternal darkness. This creates a stark contrast in temperatures, with the star-facing side being blisteringly hot while the night side is freezing cold. In some cases, powerful winds could distribute heat around the planet, creating strange, dynamic weather systems that we can barely comprehend. One particularly extreme example is WASP-12b, a low-albedo exoplanet that is being actively consumed by its parent star. This planet orbits so closely to its star that it is being stretched into an elongated shape by intense gravitational forces, slowly losing its outer layers to the star's gravity. Scientists believe that the material being stripped away from WASP-12b could be forming a glowing halo around the planet, further obscuring its true appearance. The discovery of dark exoplanets also has major implications for the search for extraterrestrial life. Traditionally, scientists have focused on detecting planets that reflect light, as they are easier to study with our current telescopes. However, if large numbers of planets are nearly invisible, we could be missing entire categories of potentially habitable worlds. Some dark planets could have thick, heat-trapping atmospheres that create stable conditions for life, even in seemingly inhospitable regions of space. If some of these planets harbor life, it might look very different from anything we know. Organisms on a low-albedo world would need to adapt to extreme darkness, possibly evolving unique forms of bioluminescence or other unconventional ways of detecting their environment. Without abundant sunlight, plant-like life forms might rely on chemical processes rather than photosynthesis, leading to entirely new biological structures and ecosystems. The prospect of life existing in such an alien environment is both thrilling and deeply mysterious. Beyond the natural explanations, there is also the possibility that some of these planets could be artificial. What if an advanced civilization deliberately altered the surface or atmosphere of a planet to make it nearly undetectable? A civilization capable of modifying an entire planet might have various reasons for doing so, whether for energy efficiency, climate control, or even strategic defense. A perfectly dark planet would be difficult to spot from great distances, making it an ideal hiding place for a highly advanced society. This idea leads to even more mind-bending possibilities. Could some of these black planets be enormous, artificial megastructures? What if an advanced species created a massive, planet-sized construct covered in materials that absorb all light and radiation? Such a structure could serve as a space station, an interstellar ark, or even a hidden outpost designed to avoid detection. If any of these dark exoplanets turn out to be artificial in origin, it would change everything we know about extraterrestrial intelligence. As our technology advances, we will likely develop new ways to study these planets in greater detail. The James Webb Space Telescope and future missions will allow astronomers to peer into the atmospheres of these mysterious worlds, analyzing their chemical compositions and searching for signs of activity. Infrared observations, spectroscopic analysis, and direct imaging techniques will reveal whether these planets are truly lifeless, or if something strange is happening beneath their light-absorbing exteriors. Perhaps the most exciting part of this mystery is that we are only scratching the surface. Low-albedo exoplanets challenge our assumptions, push the boundaries of what we thought was possible, and force us to rethink our place in the cosmos. Are they common or rare? Are they lifeless wastelands or homes to alien civilizations? Are they natural or something far more mysterious? Until we develop better ways to observe them, they will remain some of the most elusive and intriguing objects in the universe. For now, all we can do is continue searching, refining our methods, and expanding our understanding of these enigmatic worlds. The answer is out there, waiting to be uncovered. And when we finally solve the mystery of low-albedo exoplanets, it may be one of the greatest discoveries in the history of science. There is something deeply unsettling about the idea that entire worlds could be lurking in the darkness, nearly undetectable by our instruments. If low-albedo exoplanets are more common than we think, it means that our current methods of detecting planets might be overlooking an entire class of celestial bodies. For years, astronomers have focused on planets that reflect light or emit radiation in predictable ways. But what if the universe is teeming with planets that absorb almost all the light that reaches them? What if some of the most mysterious and fascinating worlds in existence are the ones we can barely see? One of the biggest challenges in studying these planets is that their darkness makes them almost invisible in optical wavelengths. Most exoplanets are discovered using the transit method, which detects a planet when it passes in front of its host star, causing a slight dip in brightness. However, if a planet is extremely dark, it might reflect so little light that even these dips are difficult to detect. The radial velocity method, which measures the gravitational influence of a planet on its star, can still reveal their presence, but it provides far less detail about their composition. This means that even when we do detect a low-albedo exoplanet, understanding what it is made of becomes a major challenge. Without the ability to observe reflected light, astronomers must rely on other techniques, such as studying how the planet's atmosphere interacts with infrared radiation. This is where telescopes like the James Webb Space Telescope, JWST, come into play. Unlike optical telescopes, JWST is designed to see in infrared, allowing it to peer through the darkness and analyze the chemical signatures of distant exoplanets. One of the most intriguing possibilities is that some low-albedo exoplanets might be hiding in plain sight. If a planet absorbs nearly all the light it receives, it could be located in a system that has already been studied, yet it remains undetected because it doesn't emit enough visible radiation. Astronomers may have already observed these systems without realizing that an ultra-dark world is lurking within them. As we refine our observational techniques, we may begin uncovering these hidden planets in surprising locations. Another major question is how these planets form in the first place. Conventional models of planetary formation suggest that planets should have a variety of reflective surfaces, from icy clouds to rocky terrain. So what makes a planet so dark that it reflects almost nothing? One possibility is that these planets have atmospheres rich in compounds that absorb most wavelengths of light. Elements like sodium, potassium, and gaseous metals could create a thick, heat-trapping blanket that prevents light from escaping. Some exoplanets may also have surfaces covered in dark, light-absorbing materials. On Earth, we see similar effects in volcanic rock and soot, which absorb more sunlight than lighter-colored surfaces. A planet covered in volcanic ash, for example, might appear almost completely black from space. In extreme cases, a planet could be coated in exotic carbon-based compounds, creating a surface that absorbs nearly all visible light. But the mystery deepens when we consider planets like Trace 2b, which is darker than coal yet orbits a star at an incredibly close distance. With so much incoming radiation, one might expect the planet to have some level of reflectivity. However, its darkness suggests that powerful atmospheric processes are at play, actively preventing light from bouncing back into space. Some researchers have even speculated that Trace 2b's atmosphere might contain unknown chemical reactions that have yet to be observed anywhere else in the universe. If these planets absorb nearly all light, does that mean they are hotter than other planets in similar orbits? Not necessarily. While some low-albedo exoplanets are indeed scorching hot, others may be colder than expected due to how their atmospheres trap and distribute heat. A dark planet that lacks a strong greenhouse effect might absorb light but fail to retain warmth, leading to extreme temperature fluctuations between its day and night sides. One of the most mind-bending possibilities is that some of these dark planets could be artificial. The idea of an alien civilization deliberately altering a planet to make it invisible might sound like science fiction, but in a universe as vast as ours, it cannot be ruled out entirely. If a highly advanced civilization wanted to hide its presence, modifying a planet's surface to absorb all incoming light would be a logical step. This could be achieved through massive-scale engineering projects, such as coating the planet in nanomaterials designed to absorb radiation. There is even the possibility that some of these planets are not planets at all, but massive structures built by advanced beings. The concept of a Dyson sphere, a megastructure designed to capture the energy of a star, has been widely discussed in theoretical astrophysics. If an alien civilization were capable of building a structure on a planetary scale, it might choose to construct it from materials that prevent detection. A planet-sized object with an ultra-dark surface could be mistaken for a low-albedo exoplanet when, in reality, it is something far more artificial. Some scientists have even proposed that such dark exoplanets could be cloaked worlds, intentionally designed to be undetectable by light-based observations. If an advanced species had the technology to manipulate light, they could create planets that are effectively invisible to anyone looking for them. This could mean that we are living in a universe where entire civilizations exist in the shadows, hiding from view. Beyond the scientific implications, the existence of low-albedo exoplanets has philosophical consequences as well. The fact that these planets are so difficult to detect raises the possibility that there are countless more worlds out there that we have yet to find. If even a small percentage of planets in the universe are nearly invisible, our current estimates of planetary populations could be drastically underestimated. This also means that our search for life must evolve. For years, astrobiologists have focused on planets that resemble Earth, worlds with blue skies, reflective oceans, and visible cloud cover. But what if life exists on planets that are almost completely black? What if entire ecosystems have evolved in permanent darkness, relying on chemical energy instead of sunlight? Such a discovery would completely redefine our understanding of habitability. Future missions will need to account for the possibility of dark planets. Instead of relying solely on visible light observations, we will need to expand our search into infrared and other wavelengths. Telescopes capable of detecting heat signatures will be essential in identifying these elusive worlds. Additionally, advances in spectroscopy could allow us to analyze the atmospheres of low-albedo exoplanets with greater precision, giving us a clearer picture of what they are made of. In the coming decades, we may finally uncover the true nature of these mysterious planets. Will they turn out to be natural formations, shaped by unique chemical and atmospheric conditions? Or will we find evidence of something far more unexpected, signs of artificial structures, cloaked worlds, or even alien megacities? The search for low-albedo exoplanets is just beginning, and with each new discovery, we move closer to answering some of the biggest questions in astronomy. For now, these planets remain among the most enigmatic objects in the universe, lurking in the shadows, waiting to reveal their secrets. The more we think about low-albedo exoplanets, the more we realize how little we truly know about the diversity of worlds beyond our solar system. If these dark planets are as common as some scientists suspect, then our understanding of planetary formation, atmospheres, and even the fundamental physics of light absorption may need to be re-examined. What makes a planet nearly invisible? How do these worlds maintain their darkness across billions of years? And most intriguingly, could some of them be hiding more than just their surface details? One of the strangest things about these planets is how they seem to defy expectations. We tend to associate darkness with coldness, yet some of the most well-known low-albedo exoplanets, like Trace 2b, are among the hottest we've ever detected. This tells us that albedo isn't just a reflection of surface temperature, it's a complex interplay between atmospheric composition, energy absorption, and heat redistribution. The reason Trace 2b is so dark may not be because it lacks reflective clouds, but because something in its atmosphere is actively trapping light. This is where the real mystery begins. Many low-albedo exoplanets likely have thick, turbulent atmospheres filled with exotic chemicals that we've never encountered in our own solar system. On Earth, we see similar effects in volcanic eruptions, where ash clouds can turn the sky pitch black. But what if an entire planet's atmosphere was permanently filled with light-absorbing particles? Imagine a world where high-altitude storms create a never-ending layer of black soot-like haze, preventing any reflection of light. One strong candidate for such an effect is titanium oxide, a chemical that has been detected in the atmospheres of some hot Jupiters. Unlike Earth's atmosphere, which scatters blue light and creates our bright sky, an atmosphere filled with titanium oxide would absorb vast amounts of radiation, making the planet appear incredibly dark. Other possible contributors include vaporized metals like iron and magnesium, which could create dense clouds that absorb instead of reflect light. But here's where it gets even stranger. Some theories suggest that these planets might not just be absorbing light passively, they could have active atmospheric processes that remove any reflective materials. If high-altitude winds constantly strip away bright clouds, leaving only dark, heat-absorbing layers behind, then even a planet that starts out reflective could become darker over time. This would explain why some exoplanets appear so black despite receiving intense radiation from their stars. However, not all dark planets are close to their stars. Some low-albedo exoplanets might be located much farther away, where the lack of sunlight makes them naturally difficult to detect. If a planet is already absorbing nearly all the light that reaches it, and it orbits in a dim region of space, then spotting it becomes nearly impossible using traditional optical methods. These planets could be hidden in the outskirts of distant star systems, or even floating alone in interstellar space, unbound to any sun. That raises another possibility. What if some low-albedo exoplanets aren't exoplanets at all, but rogue planets drifting through the galaxy? Rogue planets are worlds that have been ejected from their original star systems and now wander the cosmos alone. Without a nearby star to illuminate them, these planets would be nearly undetectable, appearing only as faint infrared signatures. If they also have atmospheres filled with light-absorbing chemicals, then even infrared telescopes might struggle to find them. This means that our current count of exoplanets might be missing an entire class of objects, dark, free-floating worlds that roam the galaxy unseen. If rogue planets are as common as some estimates suggest, then the universe could be filled with more planets than stars, most of them hidden in the cold depths of space. And here's where things take a truly mind-blowing turn. If a planet is nearly invisible, could it be intentionally hidden? This question takes us into the realm of speculative science, but it's not as far-fetched as it sounds. If an advanced civilization wanted to avoid detection, one of the simplest ways to do so would be to make their planet absorb as much light as possible. A planet that reflects no light would be almost impossible to see, even for highly developed extraterrestrial observers. This could be achieved through massive-scale engineering projects, such as coating a planet in materials that absorb nearly all radiation. Nanotechnology could allow for the creation of ultra-dark surfaces that function similarly to vantablack, the darkest material ever created on Earth. If a civilization were advanced enough to manipulate planetary-scale environments, it could theoretically design a world that is functionally invisible from a distance. There's even the idea that some of these planets might not be planets at all, but artificial megastructures. Imagine a massive space station, larger than Earth, designed to capture energy from a nearby star while remaining undetectable. Such a structure would need to absorb nearly all incoming light to avoid giving off any obvious signals. This would explain why some low-albedo exoplanets appear darker than anything we've seen in nature. While we don't have evidence of artificial planets yet, the fact remains that low-albedo exoplanets challenge many of our assumptions about how planets should look. The more we study them, the more we realize that the universe is full of surprises. Whether these worlds are naturally occurring or something far more mysterious, they remind us that space is still largely unexplored. Future telescopes will be key to solving these mysteries. The James Webb Space Telescope is already providing deeper insights into exoplanet atmospheres, and upcoming missions like the Extremely Large Telescope, ELT, and the Habitable Worlds Observatory will allow us to see distant planets in unprecedented detail. These instruments may finally allow us to pierce the darkness and uncover the secrets of these enigmatic worlds. Until then, low-albedo exoplanets remain some of the most intriguing objects in the cosmos, silent, hidden, and waiting to be found. Their existence raises profound questions about planetary evolution, atmospheric chemistry, and even the possibility of hidden civilizations. The more we learn, the more we realize just how little we truly know. The idea that low-albedo exoplanets could be more than just naturally occurring phenomena leads to even deeper questions. What if some of these dark worlds are relics of cosmic events we don't yet understand? Could they be remnants of failed star systems, where conditions prevented the formation of bright, reflective clouds? Or could they be the result of unknown chemical processes that turn once bright planets into these dark enigmas over time? One of the most fascinating aspects of low-albedo exoplanets is that they challenge our perception of what a planet should look like. We are used to the bright blues and whites of Earth, the rusty red of Mars, the swirling storms of Jupiter. Even in our own solar system, we have reflective surfaces like Saturn's icy moon Enceladus, which shines brilliantly due to its frozen exterior. So why do some exoplanets appear to reject all light? The answer might lie in their extreme environments. Let's consider hot Jupiters again, gas giants that orbit perilously close to their stars. These planets endure extreme radiation, temperatures reaching thousands of degrees, and atmospheric conditions that are unlike anything in our solar system. It's possible that their intense heat destroys cloud formations that would otherwise reflect light, leaving only dark, light-absorbing gases behind. But not all low-albedo exoplanets are gas giants. Some could be rocky worlds with surfaces covered in exotic materials. Imagine a planet where the surface is coated in a layer of pitch-black minerals, similar to the darkest volcanic rock found on Earth. Such a world wouldn't need a thick atmosphere to appear dark. It would simply absorb almost all light naturally. This brings us to the question of composition. What materials could make a planet so dark that it reflects nearly nothing? One possibility is carbon. We know that carbon-rich planets could theoretically exist, where graphite and even diamond could make up a significant portion of the crust. If a planet were covered in carbon-based compounds, it could resemble a giant lump of coal, absorbing nearly all light that hits it. Another possibility is that these planets are covered in tar-like substances. On Earth, we have natural bitumen, thick, sticky deposits that are nearly black. If an exoplanet had a similar surface, perhaps due to organic chemical reactions or geological processes, it could be an entire world of darkness. But let's step back from physical explanations for a moment, and consider a more mind-bending idea. What if these planets don't just absorb light, they actively suppress it? Could there be unknown quantum effects at play, where light behaves differently in the atmospheres of these worlds? Could electromagnetic fields or exotic particles be involved in ways we haven't yet discovered? Some physicists have speculated about the existence of naturally occurring metamaterials, substances that manipulate light in unusual ways. If such materials exist on an exoplanetary scale, they could effectively render a planet almost invisible. This would be an entirely new form of planetary science, one that forces us to rethink how light interacts with matter in extreme environments. Then there's the question of energy. If a planet is absorbing nearly all light that reaches it, where does that energy go? Does it get trapped in the atmosphere? Is it re-emitted as heat? Or could some planets have unknown mechanisms for dispersing energy in ways we don't yet understand? And here's where the speculation takes a wild turn. If energy is being absorbed and not re-emitted in expected ways, could it be used for something? Could there be a process, natural or artificial, that is harvesting light energy for unknown purposes? This connects back to the idea of low-albedo exoplanets being potential sites of advanced civilizations. A highly intelligent species, if it wanted to avoid detection, might engineer its planet to be as non-reflective as possible. The ability to absorb nearly all incoming light could be an intentional strategy, whether for energy collection, camouflage, or something beyond our comprehension. While this might sound like science fiction, there's a practical reason to consider it. If we are searching for extraterrestrial civilizations, most of our efforts focus on looking for bright signals, radio transmissions, infrared emissions, or unusual optical patterns. But what if some civilizations don't want to be found? What if their entire strategy is to be as dark as possible, blending seamlessly into the blackness of space? There's even a hypothesis that some planets could act as stealth worlds, hiding their presence from others by deliberately manipulating their albedo. If an intelligent species wanted to avoid detection, making their planet appear completely dark would be an effective way to do it. Of course, we don't need alien megastructures to make these planets interesting. The very fact that they exist in such extreme forms raises questions about how planets evolve under different conditions. It also forces us to consider how many dark worlds might be lurking just beyond our ability to detect them. Our current exoplanet detection methods rely heavily on light. We find planets by measuring how much starlight they block when they pass in front of their stars, or by observing how their gravity affects the motion of their parent stars. But if a planet is exceptionally dark and doesn't transit in a way that's easy to measure, it could remain hidden for centuries. This means that our list of known exoplanets is likely just the tip of the iceberg. For every planet we've found, there could be countless others, ones that don't give off the reflective signatures we expect, ones that exist in the shadows of their systems, waiting to be discovered. Future technology will be key in revealing these hidden worlds. Advanced telescopes with better infrared capabilities will allow us to detect heat signatures from even the darkest planets. Missions designed to study atmospheric compositions in detail could uncover the true nature of these enigmatic worlds. But the real question is, what else are we missing? If low-albedo exoplanets are so hard to detect, then how many of them are out there? Could some of the strangest planets in the universe still be beyond our reach, waiting for the next great discovery to finally bring them into the light? If low-albedo exoplanets are far more common than we currently realize, then the universe might be filled with planets hiding in plain sight. But what does this mean for our understanding of planetary formation? For decades, scientists have relied on models that suggest planets form with a mix of rocky, gaseous, and icy materials, creating diverse atmospheres and surface compositions. However, the existence of ultra-dark exoplanets challenges these models, suggesting that some planets develop in ways we never predicted. One of the biggest mysteries surrounding these planets is how they maintain their extreme darkness over time. If a planet is covered in dark materials, carbon compounds, metals, or exotic substances, it raises the question of how those materials formed in such vast quantities. Could these planets have originated in carbon-rich regions of their solar systems, where conditions favored the development of non-reflective surfaces? Or could their darkness be a result of long-term atmospheric evolution, where chemical reactions in high-pressure environments gradually darkened their outer layers? Some scientists speculate that low-albedo exoplanets might have once been more reflective, only to lose their bright cloud cover due to extreme heat, radiation, or even cataclysmic impacts. Imagine a planet that started with a brilliant, reflective atmosphere but was slowly stripped of its lighter elements due to intense stellar winds or violent cosmic events. Over millions of years, what was once a bright, Earth-like world could become a featureless black void, reflecting nothing back to space. But what if some of these planets are more than just dark? They could be completely black holes in terms of visible light. There's a possibility that certain exoplanets are so efficient at absorbing radiation that they produce little to no optical signature, making them nearly impossible to detect with traditional telescopes. If such planets exist, they could be among the most elusive objects in the universe, escaping all but the most sensitive detection methods. This brings us to an even stranger idea. Could low-albedo exoplanets be linked to exotic physics? Some researchers have speculated about the existence of materials that interact with light in unusual ways, such as substances that bend, scatter, or trap light in ways that defy our current understanding. If such materials exist on a planetary scale, they could create worlds that are not only dark but functionally invisible to traditional observational methods. There's also the possibility that some of these planets have atmospheres so dense and complex that light simply cannot escape in a way that makes detection easy. Imagine a planet where the upper atmosphere consists of swirling, chaotic layers of metallic hydrogen, absorbing all incoming light before it ever has a chance to reflect back into space. In such a case, even if the planet itself isn't composed of dark materials, its atmosphere could render it nearly indistinguishable from the darkness of space. Another perplexing aspect of these exoplanets is their potential climates. If a planet absorbs nearly all incoming light, does it become an inferno of heat, or does its atmosphere allow for heat dissipation in unexpected ways? The answer depends largely on the planet's atmospheric composition. Some scientists believe that extremely dark planets might have complex convection systems that transport heat across the entire planet, preventing any one region from becoming too extreme. Others suggest that the lack of reflected light could mean these planets radiate energy in the infrared spectrum far more efficiently than expected. This raises a critical question: could low-albedo exoplanets actually be some of the most habitable worlds in the universe? While it may seem counterintuitive, a dark planet with the right atmospheric conditions could maintain a stable climate, making it more hospitable than planets with wild temperature fluctuations. If an exoplanet's thick atmosphere is able to distribute heat evenly across its surface, it could theoretically support life, even in regions where we wouldn't expect it. But what kind of life could survive on a world that reflects almost no light? If these planets are truly dark, any life forms that evolve there would likely be adapted to low-light conditions, potentially relying on infrared vision or alternative biological mechanisms for sensing their environment. Instead of photosynthesis, which requires light, organisms on these worlds might rely on chemosynthesis, extracting energy from chemical reactions rather than sunlight. Deep-sea life on Earth provides a fascinating comparison. In the deepest parts of our oceans, where sunlight never reaches, life thrives around hydrothermal vents, feeding off the chemical energy produced by the Earth's interior. Could similar processes be at work on dark exoplanets? Could alien ecosystems exist in perpetual twilight, feeding off geothermal energy or exotic chemical processes unique to their worlds? And here's where things get even more speculative. If life does exist on these planets, could it be radically different from anything we've imagined? Could some low-albedo exoplanets harbor life forms that are biologically adapted to absorb and process light in ways beyond our understanding? Perhaps some of these life forms don't just survive in darkness. They thrive in it, evolving in ways that take advantage of their planet's ability to absorb nearly all incoming radiation. But the biggest question remains: how many of these planets are out there? If low-albedo exoplanets are as common as some scientists suspect, then they could represent an entirely new class of worlds, ones that have gone unnoticed due to their elusive nature. And if we've missed them in our surveys so far, what other cosmic mysteries are still hiding in the darkness? As our detection methods improve, the answers to these questions may soon be within our reach. With next-generation telescopes capable of analyzing planetary atmospheres in unprecedented detail, we may finally uncover the true nature of these dark worlds. Until then, low-albedo exoplanets remain one of the greatest mysteries of space, hidden in the shadows, waiting to be discovered. The deeper we dive into the mystery of low-albedo exoplanets, the more questions emerge. Could these planets exist in greater numbers than we ever anticipated, quietly orbiting their stars without revealing themselves? If so, what does that mean for our search for habitable worlds, or even for alien civilizations? One of the most intriguing possibilities is that some of these planets might be deliberately engineered to be dark. While this idea might seem straight out of science fiction, it's worth considering. If an advanced extraterrestrial civilization wanted to hide its planet from prying eyes, lowering its albedo would be an effective strategy. A planet that absorbs nearly all incoming light would be nearly invisible to our current detection methods, making it far harder to detect than brighter, more reflective planets. This concept is sometimes discussed in the context of the Fermi paradox, the question of why, despite the vastness of the universe, we have yet to detect any signs of intelligent life. One possible answer is that advanced civilizations might actively work to remain hidden. If a civilization wanted to avoid detection, making its planet as dark as possible could be a simple yet effective solution. Could some of the low-albedo exoplanets we've detected be artificially darkened worlds, designed to blend into the cosmic background? Beyond the question of artificial design, there's another possibility. Could these planets be home to bizarre, exotic matter? Some theoretical models propose the existence of substances that absorb almost all light across multiple wavelengths, far beyond what we currently understand. If such materials exist naturally, they could coat entire planets, creating worlds that are nearly undetectable with conventional astronomical methods. One fascinating candidate for such a substance is black graphene, a theoretical form of carbon-based material that could be even darker than the darkest known substances on Earth. If entire planets were coated in such materials, perhaps through volcanic activity, atmospheric reactions, or even biological processes, then their darkness could be explained without requiring artificial engineering. And then there's the question of magnetic fields. Some low-albedo exoplanets might have powerful magnetic fields that interact with their atmospheres in unexpected ways, affecting how they absorb and emit radiation. If these magnetic interactions influence the planet's ability to reflect light, they could contribute to the planet's near invisibility. In some extreme cases, these interactions could even create planetary auroras that are only visible in non-visible wavelengths, further complicating detection. But perhaps the most unexpected consequence of studying low-albedo exoplanets is how they force us to rethink planetary classification altogether. Traditionally, planets have been grouped into categories based on size, composition, and atmospheric properties. However, the existence of extremely dark planets suggests that albedo itself might be a fundamental characteristic that deserves greater attention. If we were to classify planets based on their reflectivity, we might discover entirely new trends in planetary formation and evolution. We could uncover connections between planetary darkness and stellar types, or between albedo and planetary age. Are younger planets more likely to be dark? Do dark planets tend to orbit specific types of stars? Could planetary darkness be an indicator of past cataclysms, such as asteroid impacts or extreme volcanic activity? And if we do find patterns, what might they tell us about our own solar system? Could some of the planets or moons in our own backyard have once been low-albedo worlds, only to change over time? If so, what forces shaped them into what we see today? One thing is certain: the more we study low-albedo exoplanets, the more they challenge our assumptions about the universe. They force us to ask new questions, to consider new possibilities, and to expand our understanding of what is, and isn't, possible in the vastness of space. And perhaps, as our technology improves, we'll one day detect the first truly invisible planet, a world so dark, so well hidden, that it has evaded all detection until now. What secrets might it hold? What unknown forces might have shaped it? And most importantly, what else might be lurking in the cosmic darkness, waiting to be discovered? If low-albedo exoplanets are more common than we currently realize, they could be a missing piece in our understanding of planetary formation. Traditionally, astronomers have categorized planets based on size, mass, atmospheric composition, and orbital characteristics. But what if albedo, the ability of a planet to reflect light, is just as important as any of these factors? Consider this: if a significant percentage of exoplanets have ultra-dark surfaces, it could suggest that planetary darkness is not an anomaly, but rather a common outcome of planetary evolution. Perhaps planets that form in certain regions of their star systems are more likely to accumulate dark materials. Or maybe their atmospheres evolve in ways that strip away reflective elements, leaving behind only light-absorbing compounds. One of the biggest challenges in studying these planets is that their darkness makes them difficult to observe. Traditional telescopes rely on visible light to detect exoplanets, which means that a planet that absorbs nearly all light is essentially invisible using conventional methods. Instead, astronomers must rely on indirect detection techniques, such as transit observations, watching how a planet blocks its star's light, or studying infrared emissions to detect the faint heat signatures of these elusive worlds. But what if some low-albedo exoplanets are so dark that they emit almost no detectable radiation at all? Could there be entire planetary systems that have remained hidden from us simply because they do not interact with light in a way we can easily measure? If so, then our current exoplanet catalogs may represent only a fraction of the planets that actually exist in our galaxy. This raises a fascinating possibility. If dark exoplanets are out there in large numbers, could some of them be rogue planets, worlds that have been ejected from their home star systems and now drift through the cosmos in perpetual darkness? Rogue planets are already difficult to detect, but if many of them have extremely low albedo, they could be even more elusive than we ever imagined. Some scientists speculate that there could be billions, or even trillions, of rogue planets in our galaxy, many of them completely undetectable with current technology. Imagine a world floating in interstellar space, absorbing nearly all the radiation it encounters. With no nearby star to illuminate it, this planet would be practically invisible, blending seamlessly into the darkness of the cosmos. Yet it could still be geologically active, with internal heat driving volcanoes, tectonic activity, or even subsurface oceans. Could such a world support life? If so, it would be unlike anything we've ever encountered. Another intriguing question is whether low-albedo exoplanets could provide clues about the early history of planetary systems. If some planets start out dark and gradually become more reflective over time, studying their albedo could give us insight into their age and evolutionary history. Perhaps younger planets tend to be darker, while older planets accumulate brighter materials through asteroid impacts, atmospheric changes, or other cosmic processes. And what about planetary weather? On Earth, clouds, ice caps, and changing seasons all influence how much light our planet reflects. Could dark exoplanets have dynamic weather systems that affect their albedo? If a planet's atmosphere is constantly shifting, it could mean that its darkness fluctuates over time. One year, it might appear nearly invisible, and another year, it might suddenly brighten due to massive storms or seasonal changes in atmospheric composition. If we could observe these planets over long periods, we might begin to see patterns, fluctuations in their darkness that tell us about their climates, their atmospheres, and even their potential for life. Could some of these planets be capable of changing their albedo in response to environmental conditions? If so, it would mean that planetary darkness is not a static trait, but a dynamic process influenced by a complex interplay of geological and atmospheric forces. This leads to an even more mind-bending idea. Could life itself play a role in shaping planetary albedo? On Earth, certain microbial life forms contribute to the reflectivity of ice and water surfaces. If life exists on low-albedo exoplanets, could it be responsible for maintaining their darkness? Perhaps these planets are covered in life forms that have evolved to absorb as much light as possible, using it for energy in ways we don't yet understand. Alternatively, what if some planets are dark because their ecosystems actively prevent light from escaping? Imagine a world where the dominant life forms have developed biological structures that trap radiation, either for warmth or for energy storage. Such a planet would appear almost completely black from space, yet it could be teeming with life beneath the surface. As we push the boundaries of exoplanet research, new telescopes and observational techniques may finally allow us to study these enigmatic worlds in greater detail. The James Webb Space Telescope, for example, is already capable of detecting faint infrared signals from distant exoplanets, potentially revealing the chemical compositions of their atmospheres. Future space telescopes, equipped with even more advanced sensors, could help us uncover the true nature of low-albedo exoplanets and determine just how many of them exist. But what happens if we find that dark exoplanets are even more common than bright ones? It would mean that our understanding of planetary formation needs a complete overhaul. It could suggest that the conditions that produce ultra-dark planets are widespread and that these worlds represent a major, yet largely unseen, component of our universe. Perhaps we have been looking at the universe in the wrong way all along. If dark exoplanets are out there in massive numbers, it could mean that our methods of searching for habitable worlds need to be reconsidered. Maybe life is more likely to exist on planets that don't reflect much light, worlds that are hidden in the shadows, thriving in conditions we once thought impossible. And if that's the case, then our search for extraterrestrial life might need to take a very different approach. Instead of looking for bright, Earth-like planets in the habitable zones of stars, we might need to focus on the dark, nearly invisible worlds that have been hiding in the background all this time. What secrets could they be holding? What discoveries are waiting for us in the darkness? And most importantly, are we truly alone, or have we simply been looking in the wrong places? If low-albedo exoplanets are far more common than we currently believe, it would suggest that the universe is teeming with planets that are nearly invisible to us. This realization would fundamentally change how we classify and study planetary systems. Instead of assuming that most planets reflect at least some of their star's light, we would have to consider the possibility that the vast majority of exoplanets are hiding in plain sight, their surfaces absorbing almost all incoming radiation. This has major implications for exoplanet detection. Currently, our most successful method for finding exoplanets is the transit method, where a planet passes in front of its star and causes a slight dimming in the star's brightness. But what if a low-albedo exoplanet absorbs so much light that the dip in brightness is too small to detect? We could be missing thousands, or even millions, of planets simply because they do not interact with light in a way that is easily measurable. One possible way to detect these hidden worlds is through gravitational microlensing, where the gravity of a planet bends and magnifies the light of a distant background star. Unlike the transit method, which requires a planet to pass directly between us and its star, gravitational microlensing can detect planets regardless of their brightness. If astronomers begin finding large numbers of dark exoplanets using this technique, it would confirm that these planets are not rare at all. They are simply difficult to observe with traditional methods. But the real question is, why are these planets so dark? There are several possible explanations. One theory is that their atmospheres contain an abundance of light-absorbing chemicals, such as sodium, potassium, or carbon-based compounds like soot. These elements could create a thick, hazy layer that absorbs most incoming light, preventing it from being reflected back into space. Another possibility is that the surface material of these planets is naturally dark, composed of iron-rich minerals, lava flows, or carbon-heavy compounds. Some of the darkest substances known to us on Earth, like charcoal, graphite, or even artificial materials like vantablack, could exist in natural forms on these planets, covering their surfaces in an almost lightless abyss. But what if there is an even stranger reason for their darkness? What if some low-albedo exoplanets are covered in exotic materials that we do not yet understand? Scientists have theorized about substances that could absorb nearly all incoming radiation, acting as natural light traps. If such materials exist in abundance on these planets, they could be absorbing and storing energy in ways we do not yet comprehend. This leads to an even more speculative idea. Could some dark exoplanets be artificial? If an advanced civilization wanted to hide a planet from detection, one way to do so would be to reduce its albedo to near zero. A planet coated in a superabsorbent material could become almost completely invisible, making it nearly impossible to detect with conventional telescopes. If extraterrestrial civilizations exist, could some of them have intentionally modified their planets to avoid detection? While this idea might sound like science fiction, it raises an important question. How many planets are we overlooking simply because our detection methods rely on light? The universe could be filled with planets that we are completely unaware of, existing just beyond the limits of our observational capabilities. If low-albedo exoplanets are abundant, it would also change how we think about planetary climate. A planet that absorbs nearly all light would likely be much hotter than a more reflective planet at the same distance from its star. This means that some of these planets could have extreme surface temperatures, with molten landscapes and atmospheres thick with vaporized metals. Others, especially those far from their stars, might have trapped heat deep within their interiors, allowing for the possibility of subsurface oceans even on planets that appear cold and lifeless from the outside. Could such planets support life? The answer depends on how life forms adapt to extreme environments. On Earth, we already see organisms that thrive in conditions once thought impossible, bacteria that survive in boiling hot springs, creatures that live under immense pressure in the deep ocean, and microbes that endure radiation levels that would be lethal to humans. If life can exist in such extremes here, why not on a dark exoplanet with an alien chemistry? One possibility is that life on these planets could be completely different from anything we know. Instead of relying on photosynthesis, which requires light, organisms on these planets might have evolved to harness other sources of energy, such as chemical reactions or geothermal heat. In deep-sea environments on Earth, certain bacteria survive by using hydrogen sulfide from hydrothermal vents. A similar process could sustain life on a low-albedo exoplanet, where energy from light is scarce but heat from the planet's interior is abundant. There is even a chance that life on these planets could evolve to interact with light in unique ways. Perhaps some organisms have developed structures that absorb and store light, much like certain deep-sea fish that produce bioluminescence. Could alien life forms on dark exoplanets have evolved to generate their own light in an otherwise pitch-black environment? If so, it could mean that the surface of some of these planets is not just dark, it might also be glowing in ways that are invisible to the human eye but detectable through infrared imaging. As new telescopes come online, such as the upcoming Extremely Large Telescope and future space observatories, astronomers may finally have the tools necessary to study these mysterious worlds in greater detail. If we find that dark exoplanets are widespread, it would force us to rethink our assumptions about planetary diversity. Instead of looking for Earth-like planets with bright, reflective surfaces, we might need to start searching for worlds that absorb nearly all light, planets that exist in the shadows, hiding their secrets from the universe. And if some of these planets do turn out to be habitable, it would mean that life in the universe is not just confined to planets that resemble Earth. It could mean that life is far more adaptable than we ever imagined, capable of thriving in conditions that seem inhospitable to us? What if we've been looking in the wrong places all along? What if the real signs of extraterrestrial life are not on bright, easily visible planets, but on the dark, hidden worlds that have been evading detection for centuries? The answers to these questions could change everything we think we know about the universe, and about our place in it. If low-albedo exoplanets turn out to be abundant, then our entire approach to searching for habitable worlds must be reconsidered. Instead of prioritizing planets that resemble Earth in reflectivity and atmospheric composition, we would have to broaden our criteria to include planets that absorb nearly all incoming light. These worlds, though seemingly lifeless and hostile, might contain the most unexpected conditions for survival, perhaps even fostering life forms adapted to complete darkness. One of the biggest challenges in detecting life on these planets is that traditional biosignatures rely on reflected light. When astronomers search for life, they often look for the presence of oxygen, methane, or other gases in a planet's atmosphere, which are usually identified by analyzing the way light interacts with those gases. But what if a low-albedo exoplanet absorbs nearly all light? The usual methods would be nearly useless. Instead, scientists would have to rely on heat signatures, chemical emissions, or even radio signals as potential indicators of life. This brings up an intriguing possibility. Could low-albedo exoplanets actually be more likely to host intelligent civilizations? A civilization that exists on a dark planet would need to find alternative ways to produce energy. They might develop bioengineered solutions, tapping into geothermal energy or chemical reactions to sustain themselves. If they achieve technological advancement, their entire way of harnessing energy could be radically different from what we are familiar with. But what if these civilizations aren't just adapting to darkness? What if they are responsible for it? The idea that a civilization could intentionally alter its planet's albedo to make it less detectable is not far-fetched. A sufficiently advanced extraterrestrial civilization might do the same on a planetary scale. By reducing the amount of light their planet reflects, they could effectively hide from outside observers, preventing detection from any civilization, including us, scanning the skies for inhabited worlds. This hypothesis aligns with the concept of a dark forest universe. According to this theory, advanced civilizations might choose to remain hidden because revealing their existence could invite unwanted attention from potentially hostile extraterrestrials. If this is true, then low-albedo exoplanets could be prime candidates for planets harboring intelligent life, civilizations that have deliberately camouflaged themselves against the vast backdrop of space. Another fascinating question is whether low-albedo exoplanets experience unique weather patterns. If a planet absorbs nearly all the light from its star, it could have an extremely hot atmosphere. Depending on the composition of the air, this could lead to strange and extreme weather conditions, hurricane-force winds that never stop, oceans of molten rock, or rain made of liquid metal. If a planet's heat is distributed unevenly due to tidal locking, where one side always faces its star while the other remains in darkness, it might have a permanent scorching hot days side and a frigid night side. The transition zone between these two extremes, the twilight zone of the planet, could be the only place where conditions are stable enough to allow for liquid water and potentially life. Some exoplanets known as hot Jupiters already display such extreme characteristics. These are gas giants that orbit incredibly close to their stars, often absorbing immense amounts of heat. Many of them have been found to be unexpectedly dark, with some reflecting less than 1% of the light they receive. This suggests that low-albedo planets could be more common than we think. But there is another angle to consider: how these planets formed in the first place. If an exoplanet has a naturally dark surface or atmosphere, it might be because of the way its system evolved. Some planetary formation models suggest that planets born closer to their stars could have lost their original atmospheres due to intense radiation, leaving behind only dark, heat-absorbing elements. Others propose that volcanic activity, asteroid impacts, or even biological processes could have gradually darkened a planet over time. If low-albedo exoplanets exist in large numbers, it raises an even bigger question: could Earth have been different? If our planet had formed under slightly different conditions, could it have been a dark world instead of the bright, reflective one we know today? And if so, would life as we know it still have emerged? These questions don't just change how we look at exoplanets. They change how we understand our own world. We have always assumed that the conditions on Earth, moderate reflectivity, a mix of oceans and land, and an atmosphere that allows just the right amount of light through, are what made life possible. But what if life can thrive in ways we never anticipated, on planets that don't resemble Earth at all? The discovery of more low-albedo exoplanets in the future could answer some of these mysteries, or introduce even more. As our technology improves and our ability to detect and analyze exoplanets expands, we may finally start to uncover just how many of these hidden worlds exist. And if we find signs of life on one of them, it could change everything we know about the nature of life in the universe. The universe might not be a bright and shining place filled with easily detectable planets. Instead, it could be a vast, shadowy expanse where the most interesting worlds remain unseen, absorbing the light, hiding in the dark, and waiting to be discovered. If low-albedo exoplanets are more common than we previously assumed, it could mean that many of our current models for planetary evolution are incomplete. We have long believed that planets form under relatively predictable conditions. Rocky planets tend to be reflective due to cloud cover or icy surfaces, while gas giants might vary in their albedo based on atmospheric composition. However, the presence of planets that absorb nearly all light suggests that planetary formation is far more complex than we thought. One of the biggest mysteries surrounding low-albedo exoplanets is their surface and atmospheric composition. What exactly makes these planets so dark? For a planet to reflect almost no light, it must be covered in materials that absorb light at an extreme rate. This could mean that its surface is rich in elements such as graphite, which is naturally dark and absorbs most incoming radiation. Alternatively, its atmosphere could be filled with high concentrations of light-absorbing chemicals like titanium dioxide, sulfur compounds, or even exotic substances we have yet to discover. A prime example of this phenomenon is Trace 2b, one of the darkest exoplanets ever discovered. This gas giant reflects less than 1% of the light that reaches it, making it darker than coal. Scientists suspect that its atmosphere contains sodium and potassium, as well as chemicals that absorb light rather than scatter it. But what if rocky planets can also exhibit this level of darkness? If a terrestrial world had the right atmospheric conditions, it could be just as light-absorbing as a gas giant, meaning entire Earth-like planets could be hiding in plain sight. Another important question is how these planets interact with their stars. Since they absorb nearly all incoming radiation, they likely experience extreme heating. This could cause their atmospheres to behave in unpredictable ways, leading to powerful winds, intense storms, or even atmospheric collapse. If a planet's surface temperature becomes too high, any atmosphere it once had might be stripped away, leaving behind a barren, blackened wasteland. But if it retains an atmosphere, the chemistry within it could be completely unlike anything seen on Earth. This leads to another interesting question. Could low-albedo planets be home to exotic forms of life? On Earth, we are accustomed to life that thrives under specific conditions: light from the sun, a breathable atmosphere, and a moderate climate. But if life exists on planets that barely reflect any light, it must have adapted to an entirely different environment. Imagine a world where plants do not rely on photosynthesis in the way we understand it. Instead of using visible light to generate energy, alien plants on these dark planets might evolve to absorb infrared radiation or other wavelengths invisible to the human eye. Such life forms might not even be green; they could be black, deep purple, or even translucent to maximize their ability to capture heat energy. And what about animal life? If these planets exist in perpetual darkness, evolution would likely favor creatures with heightened senses beyond vision. They might rely on echolocation, heat detection, or electromagnetic field perception instead of sight. On Earth, deep-sea creatures in the abyssal zone have already developed bioluminescence and other adaptations to survive in near-total darkness. If life exists on low-albedo exoplanets, it could be even more bizarre than anything we have imagined. One of the most mind-bending possibilities is that some of these planets could harbor civilizations that have adapted to their dark worlds. If an intelligent species evolved in such an environment, their entire perception of reality would be different from ours. They might not even have a concept of visible light in the way we do. Instead, their entire existence could be based on detecting heat signatures, gravitational waves, or even direct neural communication. If such civilizations exist, how would they view the universe? Would they recognize the existence of stars in the same way we do, or would they experience space as a realm defined by heat gradients and radiation rather than visible illumination? If they develop technology, their science might be completely different from our own, based on principles that have nothing to do with optics or light-based observation. And what if they have already detected us? If these civilizations are advanced, they might be using detection methods that we haven't even begun to consider. They might see Earth not as a bright, reflective planet, but as a thermal anomaly, an energy-rich world emitting artificial heat signals that stand out against the cosmic background. This raises an even more unsettling question. If they can see us, why haven't we seen them? Could it be that low-albedo exoplanets are deliberately concealing themselves? The idea that intelligent civilizations might intentionally make their planets darker to avoid detection aligns with the dark forest hypothesis. According to this theory, advanced life in the universe remains silent and hidden because revealing their location could invite destruction from other, possibly hostile, civilizations. If this is true, then the darkest planets might actually be the most inhabited. Instead of searching for bright, reflective worlds that resemble Earth, perhaps we should be looking at the ones that refuse to shine, the ones that absorb all light, hiding in the cosmic shadows. As our telescopes and detection methods improve, we may soon discover more of these hidden worlds. And when we do, we might be forced to rethink everything we know about planets, life, and the universe itself. If low-albedo exoplanets are more common than we previously assumed, the implications for astronomy and planetary science are profound. It suggests that many of our assumptions about exoplanet detection, habitability, and even the potential for life elsewhere in the universe need to be reconsidered. These planets, which absorb nearly all incoming light, challenge traditional methods of planetary observation and may indicate that many more worlds exist than we can currently perceive. One of the most striking aspects of low-albedo exoplanets is how they evade detection. Most exoplanets are discovered using the transit method, where a planet passes in front of its host star, causing a temporary dip in the star's brightness. However, planets that reflect almost no light provide very weak signals, making them harder to identify. This means that our current planetary catalogs could be heavily biased toward brighter, more reflective worlds, leaving an entire class of dark planets largely unaccounted for. Furthermore, these dark planets challenge the way we model planetary atmospheres. Traditional models assume that some level of reflection occurs due to cloud cover, atmospheric particles, or surface ice. However, if a planet absorbs nearly all incoming light, it suggests a fundamentally different atmospheric composition than what we are used to. For example, hot Jupiters with extremely low albedo likely have atmospheres dominated by metallic compounds or exotic chemical reactions that prevent light scattering. Some researchers propose that these planets could have atmospheres rich in vaporized metals, soot-like carbon compounds, or even unknown elements that interact with light in ways we have yet to understand. This also has a direct impact on planetary temperature. Since these worlds absorb most of the energy they receive from their stars, they likely experience extreme heating. This could lead to unexpected climate patterns, massive atmospheric storms, or even runaway greenhouse effects that create entirely new classes of planetary environments. For example, a low-albedo planet could have an atmosphere that traps heat so efficiently that it becomes a world of perpetual infernos, with temperatures far exceeding those of more reflective planets at the same orbital distance. Some researchers speculate that low-albedo planets could be the missing link in understanding rogue planets, worlds that drift through space without a host star. If a planet is already extremely dark and absorbs most of its radiation, it could theoretically maintain internal heat even after being ejected from its solar system. This would mean that rogue planets might not be as cold and lifeless as we assume. Instead, they could retain geothermal energy beneath thick, insulating atmospheres, creating conditions where life could persist even in interstellar space. This raises a deeper question. Could life exist on a low-albedo exoplanet despite its extreme conditions? The answer is complicated, but not impossible. We tend to associate life with conditions similar to Earth: moderate temperatures, a stable atmosphere, and access to sunlight. However, extremophiles on Earth prove that life can adapt to incredibly harsh environments. If a low-albedo planet is hot and covered in a thick atmosphere, it could create a world where microbial life thrives in high-temperature environments, much like the extremophiles found in Earth's deep-sea hydrothermal vents. These life forms could survive by harnessing chemical energy rather than relying on sunlight. Some researchers suggest that entire biospheres could exist based on chemosynthesis rather than photosynthesis, meaning that an alien ecosystem could flourish in darkness, feeding on volcanic gases, metal-rich compounds, or even the heat energy itself. But what if intelligent life evolved on one of these planets? A civilization that develops in near-total darkness would likely have evolved senses very different from ours. They might rely on heat perception, sonar-like echolocation, or even electromagnetic detection instead of sight. This would fundamentally change how they perceive the universe. Instead of developing telescopes based on light, they might have advanced technologies for detecting energy signatures, gravitational distortions, or cosmic radiation patterns. This leads to a fascinating possibility. If an advanced alien civilization exists on a low-albedo planet, their ability to detect us might be vastly superior to our ability to detect them. We rely on visible light and radio waves to search for extraterrestrial signals, but a species that evolved in darkness might use entirely different methods of communication. They could be watching us right now, aware of our existence, while we remain blind to theirs simply because we are looking for the wrong signs. And this brings us to an unsettling thought: what if low-albedo planets are deliberately dark? The dark forest hypothesis, a concept from the Search for Extraterrestrial Intelligence (SETI), suggests that advanced civilizations might actively avoid detection to prevent being targeted by hostile alien species. If this is true, then the darkest planets might be the most inhabited ones. Instead of searching for bright Earth-like worlds, perhaps we should be looking at the ones that refuse to shine, the planets that absorb all light, hiding in plain sight. As technology advances, we are getting closer to answering these questions. The James Webb Space Telescope and future observatories will allow us to analyze the atmospheres of exoplanets in more detail than ever before. If we discover more of these dark worlds, it could revolutionize our understanding of planetary science and potentially lead to the biggest discovery of all: evidence that we are not alone in the universe. The discovery of low-albedo exoplanets forces us to rethink the way we classify and study alien worlds. Traditionally, planets are often categorized based on their size, composition, and distance from their host star. But albedo, or how much light a planet reflects, may be just as crucial. A planet with a low albedo absorbs nearly all the light that hits it, making it difficult to detect and potentially harboring extreme conditions that we have never encountered before. One of the most famous low albedo exoplanets we've detected is Trace 2b, a gas giant that reflects less than 1% of the light that reaches it. That's darker than charcoal, making it one of the blackest planets ever discovered. Trace 2b is a hot Jupiter, orbiting close to its star, and its darkness is likely due to an atmosphere filled with vaporized alkaline metals, titanium oxide, or other compounds that absorb light instead of reflecting it. But here's the thing: Trace 2b is just the beginning. If one such world exists, there are probably countless others, hidden from our view simply because they are too dark to easily detect. This raises an even bigger mystery. If we're missing planets because they are so dark, what else are we missing? Could there be entire planetary systems out there that remain invisible to us, simply because they don't reflect light in a way we can see? Some researchers suspect that these dark worlds could be far more common than we ever imagined, and if that's true, it would reshape our understanding of the galaxy. Another compelling possibility is that low albedo planets could be linked to unusual chemical processes we have yet to understand. For instance, some theories suggest that these planets may have exotic atmospheric conditions, such as clouds made of sodium, potassium, or carbon-based compounds that absorb rather than scatter light. Others propose that these planets could have vast oceans of hydrocarbons, similar to Saturn's moon Titan, covering their surfaces and absorbing most of the incoming radiation. If that's the case, then some of these planets might have conditions that are surprisingly Earth-like beneath their dark exteriors. But what if a low-albedo exoplanet wasn't just naturally dark? What if something, perhaps an advanced civilization, was intentionally making it that way? This idea, while speculative, ties into the concept of artificial megastructures, like Dyson spheres or other technological constructs designed to harness energy or hide a planet from detection. If a civilization wanted to remain undetectable, making their planet absorb nearly all light would be a highly effective strategy. In the vastness of space, a planet that doesn't reflect light would be nearly invisible, even to our most advanced telescopes. This also connects to the idea of stealth civilizations. Some astronomers speculate that if extraterrestrial life exists, it might have learned to avoid detection as a survival strategy. In this scenario, civilizations that expose themselves might risk being targeted by others, leading to a galactic, dark forest scenario where intelligent beings remain silent and hidden. Could low-albedo exoplanets be evidence of such civilizations? If so, how would we ever confirm their existence? We might get some answers soon. Future telescopes like the European Extremely Large Telescope, ELT, and the Nancy Grace Roman Space Telescope will have unprecedented capabilities in detecting exoplanets, even those that are difficult to see with current technology. They could allow us to identify more low-albedo worlds, analyze their atmospheres, and potentially discover whether these planets are truly lifeless or hiding something more. Low-albedo exoplanets remain one of the biggest mysteries in modern astronomy. They challenge our assumptions, force us to rethink planetary science, and may even hold clues to the existence of extraterrestrial life. Whether they are naturally dark or intentionally hidden, these worlds could redefine our understanding of the cosmos. And if we ever find one that isn't just a lifeless rock but something far more complex, something that suggests intelligence, then the way we see the universe will change forever. If low-albedo exoplanets are more common than we once thought, it could mean that our entire model of planetary formation needs revision. Current theories suggest that planets develop albedo based on a mix of their atmospheric composition, surface materials, and distance from their host star. But if there are large numbers of planets that absorb nearly all incoming light, something else might be at play. One possibility is that these planets formed in regions of their solar systems rich in light-absorbing materials, such as carbon-heavy compounds. In our own solar system, we see hints of this with objects like the moons of Saturn and Jupiter, which have dark, carbon-rich surfaces in certain regions. If similar processes occurred on a planetary scale, some exoplanets could have entire surfaces covered in pitch-black material, making them nearly undetectable. Another theory suggests that these planets may have dynamic atmospheres with chemical processes that actively maintain their darkness. For instance, planets that are constantly bombarded with stellar radiation might develop soot-like layers in their upper atmospheres, creating a permanent shroud that absorbs incoming light. This would mean that instead of a static, dark surface, these planets are constantly being reshaped by their environment. But perhaps the most intriguing idea is that some of these planets may be far older than expected. If low-albedo planets tend to form in environments where they naturally absorb more light, it could mean that we are looking at some of the oldest planetary bodies in the galaxy, worlds that have existed long before Earth even formed. If that's the case, they might have seen entire civilizations rise and fall, their history hidden beneath the veil of darkness. This leads to another fascinating thought. Could these planets serve as natural black holes for detecting alien artifacts? If extraterrestrial civilizations existed in the past and sought to hide their presence, a low-albedo planet would be the perfect place to do it. These planets are already nearly invisible to conventional detection methods, meaning any structures or signals originating from them would be just as hidden. If we ever do detect a signal from one of these dark worlds, it might not be from a living civilization, it could be the remnants of a long-dead one. The implications for future exploration are staggering. Imagine sending a probe to one of these planets, only to find massive artificial structures buried beneath a thick, absorbing atmosphere. It would suggest that advanced civilizations not only existed but understood how to manipulate their environment in ways we can barely comprehend. The search for extraterrestrial intelligence has always focused on bright signals, radio waves, beacons, or other forms of communication. But what if the real evidence is hidden in the darkest places? Another question arises. If we were to one day colonize other worlds, would we consider making our own planet's low-albedo? A civilization that wants to avoid detection could, in theory, engineer its planet to absorb nearly all incoming light, effectively making it invisible to outside observers. This would be the ultimate form of planetary stealth technology, an entire world hidden in the blackness of space. The James Webb Space Telescope and other next-generation observatories may finally give us the ability to detect these planets in greater numbers. By studying their infrared signatures, we may be able to determine whether their darkness is due to natural processes or something more unusual. If we find one with an atmosphere that seems engineered, or a heat signature that suggests artificial structures, it could be the biggest discovery in the history of science. Low-albedo exoplanets are among the most mysterious objects in the universe. They defy detection, absorb nearly all light, and challenge our understanding of planetary science. But they also offer a new frontier for exploration. Whether they hold clues to alien life, lost civilizations, or unknown natural processes, these dark worlds may hold secrets that could change everything we know about the cosmos. If low-albedo exoplanets are more common than we think, the implications for our understanding of planetary evolution, habitability, and even extraterrestrial intelligence could be profound. These planets challenge traditional detection methods because they do not reflect light in ways that make them easy to spot. Instead of appearing as bright dots against the blackness of space, they are nearly indistinguishable from the void itself. This raises an unsettling question: how many of these planets have we already overlooked? Could they be the missing piece in our search for life beyond Earth? One of the key challenges in detecting these planets is that most of our exoplanet hunting techniques rely on light. The transit method, for example, measures dips in a star's brightness when a planet passes in front of it. But what if the planet is so dark that it blends into the background? If its albedo is close to zero, the difference in brightness might be so small that our telescopes miss it entirely. Even the radial velocity method, which detects the gravitational wobble of a star caused by orbiting planets, may struggle if the planet itself does not contribute significantly to the overall light spectrum. To get around this problem, scientists have started exploring alternative detection methods. Infrared telescopes, like the James Webb Space Telescope, can pick up heat signatures rather than visible light. Even if a planet is pitch black in the visible spectrum, it still absorbs and remits energy, meaning it could glow faintly in infrared. This approach could reveal entire populations of planets that were previously invisible, including low-albedo gas giants, rocky worlds, and potentially even rogue planets that drift through space without a host star. The existence of these dark worlds also forces us to reconsider what makes a planet habitable. Traditionally, we have assumed that habitability requires a certain level of reflected light, particularly for photosynthesis-based life. But what if there are alternative forms of life that thrive in near-total darkness? Deep in Earth's oceans, organisms survive without sunlight, relying instead on chemical energy from hydrothermal vents. Could similar processes occur on low-albedo exoplanets, where heat and chemical reactions provide the necessary energy for life to develop? Some astrobiologists speculate that low-albedo planets could have thick atmospheres filled with complex organic molecules. Instead of reflecting light, these molecules might absorb it, creating a permanent darkness that still supports a functioning biosphere. If such planets exist, they would challenge our entire definition of what it means for a planet to be alive. Another possibility is that these planets could be home to forms of life that actively contribute to their darkness. On Earth, some species of bacteria produce light-absorbing pigments to protect themselves from radiation. If a planet's dominant lifeforms evolved a similar adaptation, they might have created a naturally dark world as a survival mechanism. This would mean that, paradoxically, a planet's darkness could actually be a sign of life rather than an absence of it. The idea of artificial low-albedo planets remains one of the most tantalizing possibilities. If an advanced civilization wanted to avoid detection, it could engineer its planet to absorb nearly all incoming light, making it almost invisible to telescopes. Such a civilization might be part of the dark forest hypothesis, a theory that suggests intelligent life in the universe remains hidden to avoid potential threats. If this is true, then low-albedo planets might not just be natural oddities. They could be intentional cloaking devices for civilizations that prefer to remain unseen. This raises an even deeper question. If such civilizations exist, how would we ever find them? If they have the technology to make their planet nearly undetectable, they might also have the ability to mask other signals, such as radio waves or heat emissions. The only way to detect them might be through indirect evidence, subtle gravitational effects, unexplained heat fluctuations, or unusual chemical signatures in their atmospheres. The search for low-albedo exoplanets is just beginning, but the discoveries we make in the coming years could revolutionize our understanding of the universe. These planets could be relics of ancient solar systems, hiding places for advanced civilizations, or laboratories for exotic forms of life. Whether they are simply strange, light-absorbing worlds or something far more mysterious, they remind us that the universe is full of secrets waiting to be uncovered. If low-albedo exoplanets are hiding in plain sight, what else might we be missing? The nature of these dark worlds forces us to rethink how we search for planets, what we consider habitable, and even how we define life itself. The idea that entire planets might be invisible to traditional telescopes is unsettling. It suggests that our understanding of the universe is still extremely limited and that we might be grossly underestimating the number of worlds out there. One of the most fascinating aspects of low-albedo planets is how they interact with light. Most planets reflect at least some of the light that hits them, but these exoplanets absorb nearly all of it. This could be due to several factors: a surface covered in carbon-rich compounds, a thick atmosphere filled with light-absorbing particles, or even chemical reactions that actively prevent reflection. This unique property raises an interesting question: what happens to all that absorbed energy? When a planet absorbs large amounts of light and heat from its star, it has to release that energy somehow. Some of these planets likely emit radiation in the infrared spectrum, making them easier to detect with instruments like the James Webb Space Telescope. Others might have extreme weather systems, where heat energy is redistributed across the surface in ways we don't yet understand. This could lead to hurricanes, massive storms, or even permanent atmospheric turbulence, creating a chaotic world that operates under completely different physical principles than what we see on Earth. Imagine a planet where the atmosphere is so thick and light-absorbing that it never experiences daylight. A world where the sky is pitch black even during the day, with only the faintest red glow of thermal radiation illuminating the landscape. This might sound like science fiction, but such planets could very well exist. And if they do, what kind of creatures might call them home? On Earth, we associate life with light. Plants use photosynthesis, animals rely on vision, and entire ecosystems are built around the day-night cycle. But there are life forms deep in our oceans that live in complete darkness, using chemical energy instead of sunlight to survive. If such ecosystems exist here, why wouldn't they exist elsewhere? Low-albedo exoplanets might be home to organisms that thrive in darkness, relying on heat, pressure, and chemical interactions instead of solar energy. Some scientists have even speculated that planets with extremely low reflectivity could be artificial in nature. A civilization with advanced engineering capabilities could, in theory, construct megastructures that absorb all incoming light, creating a kind of optical cloaking device. This would allow them to remain hidden from outside observers while still harnessing energy from their star. If such civilizations exist, they might have developed entire planetary systems designed to be invisible, making our search for extraterrestrial life far more difficult than we ever imagined. Even without intelligent life, low-albedo planets could offer valuable insights into planetary formation and atmospheric chemistry. If we can determine what makes these planets so dark, we might discover new materials, unknown atmospheric processes, or even exotic elements that don't exist on Earth. These findings could have implications not just for astronomy, but for physics, chemistry, and even technology. What if we found a naturally occurring substance that absorbs more light than anything known to science? The possibilities are endless. But perhaps the biggest mystery is how many of these planets exist. If they are common, it would mean that our models of planetary formation need to be reworked. It could suggest that dark, light-absorbing planets are a natural stage in planetary evolution, or that certain types of stars are more likely to host them. If they are rare, then their existence becomes even more intriguing. It would mean that specific, unique conditions must come together to create them, conditions that might be tied to the presence of exotic chemicals, extreme radiation environments, or even artificial engineering. Regardless of how they form, one thing is certain: low-albedo exoplanets challenge everything we think we know about the universe. They force us to consider new possibilities, develop new detection methods, and question our assumptions about planetary science. And as we continue to search the cosmos, they remind us that the greatest mysteries are often the ones hiding right in front of us, waiting for the right moment to be discovered. If low-albedo exoplanets are far more common than we currently suspect, then the implications for planetary science and astrobiology are staggering. It would mean that the way we classify planets, based on their reflectivity, composition, and visibility, might be deeply flawed. We could be living in a universe where a significant percentage of planets remain completely hidden, not because they are far away, but because they are absorbing nearly all of the light that reaches them. This raises a fundamental question: why are these planets so dark? The most obvious answer is their surface composition. Planets with thick layers of carbon-rich material, such as graphite or soot-like compounds, could absorb nearly all incoming light. Titan, one of Saturn's moons, has a thick atmosphere full of complex hydrocarbons that give it a murky, orange appearance. If an exoplanet had an even denser atmosphere full of such compounds, it could be almost completely black in the visible spectrum. Another possibility is that these planets are covered in lava or liquid metals that absorb light rather than reflecting it. Some of the hottest exoplanets we've discovered, such as those orbiting extremely close to their stars, have surfaces that may be molten. If the right elements are present, iron, carbon, or exotic silicate compounds, these worlds could act like cosmic black holes for visible light, appearing as mere shadows against the glare of their host stars. But what if the darkness is caused by something even stranger? Some scientists believe that certain exoplanets could have atmospheres laced with microscopic particles that scatter and absorb light in unpredictable ways. On Earth, volcanic eruptions release fine ash and aerosols that can temporarily darken the sky. If a planet had constant volcanic activity, asteroid impacts, or even biological processes that release dark, light-absorbing compounds, it could create a self-sustaining darkness that lasts for millennia. There's also the unsettling possibility that these planets are not naturally dark, but intentionally hidden. If an advanced civilization wanted to avoid detection, reducing their planet's albedo would be an effective strategy. A species with advanced knowledge of optics and material science could engineer planetary surfaces to absorb nearly all light, making it nearly impossible for distant observers to detect them using traditional methods. This could be a survival mechanism, a way of avoiding potential threats in the universe, a concept eerily similar to the dark forest theory, which suggests that intelligent civilizations stay silent and hidden to avoid being targeted by more powerful beings. But how would we ever know if a planet was being artificially darkened? One possible clue would be heat signatures. Even if a planet absorbs nearly all visible light, it must still radiate heat in the infrared spectrum. If we detect a planet that is completely dark but emits strange, artificial-looking infrared patterns, it could suggest that something, or someone, is modifying the planet's natural thermal output. Another way to identify these planets is through their gravitational influence. Even if we can't see a planet, we can still measure its effects on nearby objects. If a star wobbles in an unusual way, or if a known exoplanet's orbit is being affected by an unseen mass, it could indicate the presence of a dark world lurking in the background. One of the biggest questions about low-albedo exoplanets is whether they could support life. At first glance, a planet that absorbs nearly all light might seem inhospitable, But life on Earth has already proven that it can adapt to extreme darkness. Deep in our oceans, entire ecosystems thrive around hydrothermal vents, using heat and chemical reactions instead of sunlight. If similar conditions exist on dark exoplanets, then life could be thriving right under our noses, completely invisible to our current methods of detection. It's also possible that life on these planets could evolve in ways we can't even imagine. On Earth, some microorganisms produce pigments that absorb light as a form of protection. What if an entire biosphere evolved to use light-absorbing compounds, not just for protection, but as a way to store and use energy in ways fundamentally different from photosynthesis? Such life forms could exist in a perpetual twilight, their biological processes optimized for a world where light is scarce and heat is the primary energy source. The more we learn about exoplanets, the more we realize that the universe is full of surprises. Low-albedo planets are one of the most mysterious and underexplored categories of worlds, and they could hold the key to understanding planetary formation, atmospheric chemistry, and even the search for extraterrestrial life. With new telescopes coming online in the coming decades, we may finally get the chance to see these dark worlds up close, and when we do, we might discover that the universe is far stranger than we ever imagined. The search for low-albedo exoplanets is not just about finding dark worlds, it's about expanding the limits of what we think is possible in planetary science. If these planets are common, it would mean that a vast number of celestial bodies have been hiding in the data all along, simply because our methods of detection weren't designed to find them. This realization forces us to rethink how we classify planets, how we study their atmospheres, and even how we define the habitable zone. One of the most fascinating aspects of these planets is their potential surface environments. Imagine a world where the ground is made of pitch black, heat-absorbing rock, stretching endlessly under a dark sky. The atmosphere could be thick with chemicals that block out nearly all visible light, creating a place where the concept of day doesn't exist. If we were to land on such a planet, we might find ourselves in a landscape where our eyes are useless, where heat and chemical reactions dictate everything, and where survival depends on navigating through a world of shadows. But what if there's more to these planets than just their darkness? Some scientists believe that low-albedo exoplanets could have extreme weather patterns unlike anything seen in our solar system. Because these planets absorb so much heat, their atmospheres might be in a constant state of turmoil, with winds faster than any storm on Earth. These winds could carry massive dust clouds made of carbon or metal particles, creating a planetary-scale storm system that never ends. And then there's the question of what these planets are made of. Are they covered in black rock? Are their atmospheres thick with soot-like particles? Or could they be composed of exotic materials we've never encountered before? Some theories suggest that certain low-albedo planets might have surfaces covered in carbon allotropes, forms of carbon arranged in unique structures that give them incredibly high light absorption properties. If so, studying these planets could lead to breakthroughs in materials science, revealing new substances with applications far beyond astronomy. But perhaps the biggest mystery is why these planets exist in the first place. Are they the result of specific planetary formation processes? Are they remnants of ancient, burned-out worlds that lost their ability to reflect light? Or are they something else entirely? Something that challenges our current models of planetary evolution? The fact that these planets are so difficult to detect means that we're only beginning to scratch the surface of this mystery. What's even more intriguing is the idea that some of these planets might not be planets at all. If an advanced civilization wanted to remain hidden, creating a completely light-absorbing structure around their world would be one way to do it. This would be far more effective than a simple cloaking device. It would make the planet practically invisible to all traditional forms of observation. If such civilizations exist, they could be hiding in the data we've already collected, masked as nothing more than statistical noise. The more we study these dark worlds, the more we realize how little we know. Every new discovery about them forces us to question our assumptions, rethink our methods, and consider possibilities that once seemed impossible. The universe is full of mysteries, and low-albedo exoplanets are among the most intriguing. As our technology improves, we may finally begin to uncover their secrets, and when we do, we may find that the truth is even stranger than we ever imagined. If low-albedo exoplanets are more common than we think, then the universe could be hiding an entire class of planets that have gone undetected for decades. The implications of this are staggering. Imagine if a significant portion of the exoplanets we've already discovered actually have dark surfaces or thick, light-absorbing atmospheres that make them far less visible than their high-albedo counterparts. This would mean that our current estimates of planetary diversity are incomplete, and that the number of exoplanets in the universe could be far greater than we ever imagined. The key challenge in detecting these worlds is that they do not reflect enough light to be seen using traditional telescopic methods. Most exoplanet detection relies on either the transit method, where a planet passes in front of its star and causes a brief dimming, or the radial velocity method, which measures the tiny gravitational tug a planet exerts on its host star. But these methods favor planets that are either large, close to their stars, or reflective enough to be detected through indirect means. Low-albedo planets, which absorb nearly all incoming light, are nearly invisible to the transit method unless their size is significant enough to block out a noticeable portion of their star's light. This is why astronomers have begun considering new ways to detect these hidden planets. One promising approach is the use of infrared telescopes, such as the James Webb Space Telescope, which can detect heat signatures rather than visible light. Even if a planet absorbs almost all incoming light, it must still emit some thermal radiation. This means that even the darkest planets should still be detectable in the infrared spectrum, assuming their temperatures are within a certain range. However, if a planet is extremely cold or if its atmosphere contains exotic compounds that efficiently trap heat, it could still remain undetectable, even in the infrared. Another possible method of detection involves gravitational microlensing. This technique relies on the bending of light caused by a massive object passing in front of a distant background star. If a dark exoplanet moves between us and a faraway star, it can momentarily magnify the star's light due to the warping of spacetime. While this method has been used to discover some of the most elusive objects in space, it requires precise timing and alignment, making it a rare but powerful tool for uncovering hidden planets. One of the strangest implications of low-albedo exoplanets is that some of them may be rogue planets, worlds that do not orbit a star at all. These planets could be wandering through interstellar space, absorbing what little light reaches them and emitting only faint traces of infrared radiation. Without a nearby star to illuminate them, they would be nearly impossible to detect with conventional telescopes. The discovery of such a planet would raise profound questions about planetary formation and the fate of rogue worlds. Are these planets ejected from their original solar systems? Are they remnants of failed planetary formation? Or could some of them be artificial structures, designed to blend into the cosmic darkness? The possibility of artificial low-albedo planets is a concept that has intrigued scientists and science fiction writers alike. If a highly advanced civilization wanted to remain undetectable, creating a planet with an almost perfectly light-absorbing surface would be one way to achieve that goal. Such a civilization might construct a planetary-scale stealth system, using engineered materials designed to absorb and dissipate all incoming light, making their world nearly invisible. This could be done for defensive purposes, to avoid detection from other potentially hostile civilizations, or as part of some unknown cosmic experiment. Even without assuming intelligent design, the existence of ultra-dark planets suggests that planetary diversity is far greater than we once believed. The universe is full of extreme conditions, from ultra-hot gas giants to frozen ocean worlds, and low-albedo planets add yet another layer of complexity to this cosmic puzzle. Some of these planets may be relics of ancient solar systems, their surfaces blackened by eons of asteroid impacts, volcanic activity, or chemical reactions that have coated them in light-absorbing substances. Others may be shrouded in atmospheres so thick and turbulent that no light can escape, creating a planet-sized black hole in the visible spectrum. The study of these planets could have practical applications beyond astronomy. If we discover materials on these worlds that have unprecedented light-absorbing properties, they could revolutionize everything. Scientists have already created synthetic materials on Earth that can absorb nearly all incoming light, such as vantablack, a substance made of tightly packed carbon nanotubes that absorb 99.965% of visible light. If nature has created something even darker on a planetary scale, studying these materials could lead to breakthroughs in physics and engineering. As our telescopes become more advanced, we may finally get a closer look at these enigmatic planets. The next generation of space observatories, such as the Nancy Grace Roman Space Telescope and proposed exoplanet-focused missions, could provide us with the tools needed to detect and study these worlds in greater detail. We may find that these planets are far more common than we ever expected, or we may discover something even stranger, something that forces us to rethink everything we know about planetary science. The universe is a vast, mysterious place, and low-albedo exoplanets are just one of the many hidden secrets waiting to be uncovered. Whether they are barren, carbon-coated wastelands, storm-ridden gas giants, or something entirely different, their existence challenges our understanding of what planets can be. And as we continue our search for them, we may stumble upon discoveries that rewrite the rules of astrophysics, and perhaps even the nature of life itself. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.